good to, try to
All
be as
right,
practical as
everybody.
possible.
What is
Because I think a lot.
Let me just pause it. And I forgot to change the title and everything, so I will do that real quick. So in this stream, learning about, let me just verify what I'm learning about. Algorithms, okay. Algorithms. And you might ask why. Um, Let me just create a reason real quick. To enhance my capabilities. I don't really know how to spell that, so that's a different issue. I totally knew it. I was just lying. So, anyways, the main reason I'm doing this is because I am bored, need to do something good, something good, and let's get started. See, I have a ping, and I will need to check that out. Otherwise, I might get fired. So, give me a second. And amazing! As soon as I changed the screen, it showed the Discord. I was about to. And uh, yes. Let me think. What should I reply? Yes. We push that command for what should I say? This is painful. Just give me a second, guys. I'm replying to people and I don't know what to say, so it's painful. What should I say? Okay, now I have a phone. That sucks. Give me a second, man. All right. So the call is from United Kingdom, and I don't really know anyone from United Kingdom, so that's very interesting. And I don't know. Well, most likely it might be a scammer or something. So no comments on that. Oh wait, I forgot to reply to WhatsApp. Give me a second. Okay. Let me just reply real quick. Let me close my browser real quick. Now I need to go to Discord. Okay, the reply is done. Ah, wait, did I show you my? Oh, I'm so dumb. But anyways, who cares? First of all, I need to switch this into a live chat and send a hello world message. And I need to check my messages once more. Amazing. Just give me a few more seconds. Uh,
23. She left her body in Harvard above.
Seeing monsters out your window. No, you can't sleep, you pretend though. You don't have to play the hero. 'Cause I got you like you got me. When the earth shakes, when the bombs scream, until our last breath, every heartbeat. you knew. Restless every time we start looking as a lost control. Oh, it's paradise with honesty, but I'm in the dead of the night. Let the darkness take control. Let the darkness take control. Darkness take control. May the darkness take control. Take me in the smoke, breathe me in and let me go. Sink to your heart to find you. Open up your eyes till you're blinded by the lies, so you can see what you do. Restless every time we start looking as a lost control. Oh, it's paradise with honesty, but I'm in the dead of the night. Teardrops on the floor. The pain is over. Feel the darkness take control. Darkness take control.
I live inside my own world of make-believe. Kids screaming in the cradles, profanities. I see the world through ice covered in ink and bleach. Cross out the ones who heard my cries and watched me weep. I love everything. Fire spreading all around my room. My world's so bright, it's hard to breathe, but that's alright. Hush. Tape my eyes open to force reality. Why can't you just let me eat my weight in glee? I live inside my own world of make-believe. Kids screaming in their cradles, profanities. Some days I feel skinnier than all the other days. Sometimes I can't tell if my body belongs to me. I love everything. Fire spreading all around my room. My world's so bright, it's hard to breathe, but that's alright. Hush. Hold your breath and feel the tension. one too many quarters in my pockets. Count 'em like the four-leaf clovers in my locket. Untied laces, yeah. Just tripping on daydreams. Got dirty little lullabies playing on repeat. Might as well just ride around the nursery and count sheep.
When there's no hope hiding, no chance concealing what deep down I felt for you. Oh, I regret for losing the one who loved me, for who I can't go back to. Walking through all the dust, memories and frame, a past we simply let fade. Oh, but I don't close the door, waiting a chance for when we'll be back again. You make me feel so crazy, still in love with you. You make me feel amazing when I'm next to you. You make me feel so crazy, my heart breaks for you. Can't help but know that I'm still in love with you. You make me feel so. When there's no hope loving for you, who saw me before I knew who I'd be. What I have around me means nothing to me if I can't share it with you. Walking through all the dust, memories and frame, a past we simply let fade. But I don't close the door, waiting a chance for when we'll be back again. You make me feel so crazy, still in love with you. You make me feel amazing when I'm next to you. You make me feel so crazy, my heart breaks for you. Can't help but know that I'm still in love with you. You make me feel so. Fallen one too many times, feeling like it never ends. Back again, square one. Tried to leave myself behind, looking for a better place, not to stay alone. Gain our trust and you chose to break it. Asked for truth, but you only fake it. Thought you said what we had was sacred. It's all lies, all lies. I was broken and isolated, but inside held the fire waiting. Not a word that you say can save us, so don't try. 'Cause this time you crossed the line. This time you crossed the line. girls with their nails done. Girls with their nails done. And the girls with their nails done. Girls with their girls with their nails done. 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 Girls with their girls with their nails done.
Got a monster inside of me, you better watch out. If your enemy's a road ahead, a full prophecy to be the greatest beast the world has ever seen. I feed him every day like the bones clean. I feed him all the hate and he throws me. And he gets caught real big, pissed off quick. And if you cross him, you might drop dead. Metaphorically, of course, settling this war, never getting bored. Loves the blood and gore, always wanting more freedom from the source. They don't really understand until they feel the force departed. If you start shit, you'll be heartless in the darkness. Torn apart quick, you left scars ripped to be chewed up and discarded.
And this world ain't right, won't accept it. Negative energy, I expect it. Once it's in your mind, it's infectious. So fight for your life and reject it. You better give me space, I'm protected. My adrenaline spikes when I'm threatened. And if you stay in my way, I'm aggressive. Cause when there's no legs, it'll kill when I'm desperate.
He's back and better than ever. I can feel my heart rate, adrenaline pressure. It's stormy weather, lightning, thunder, pouring weather. Yo, I'm a go-getter, try to do it like me, but I do it better. I got a mind that's clever, the beast inside is competitive as ever. I'm conscious, my subconscious, an accomplice to me. I promise the darkness, I can honestly. But don't cross me, I might lose control of the lost beast. So, he's locked away inside with the key control, by fight or flight.
And this world ain't right, won't accept it. Negative energy, I expect it. Once it's in your mind, it's infectious. So fight for your life and reject it. You better give me space, I'm protective. My adrenaline spikes when I'm threatened. And
if you stay in my way, I'm aggressive. Cause when there's no exit, I'll kill when I'm desperate. Cause when there's no exit, I'll kill when I'm desperate. Cause when there's no exit, I'll kill when I'm desperate. Exit, I'll kill when I'm desperate. Exit, I'll kill.
Devil in a red dress. Call 911, I'm a killer. You know I had to confess. Bang, bang, got my hand on the trigger. The devil in a red dress. Call 911, I'm a killer. You know I had to confess. Bang, bang, got my hand, bang, got my hand, call Devil in a red dress. Call 911, I'm a killer. You know I had to confess. Bang, bang, got my hand on the trigger. The devil in a red dress. Call 911, I'm a killer. You know I had to confess. Bang, bang, call
When you want to get off that darkest ground, but gravity pulls you straight down. Earth from a bird's eye view. You should grow feathers and see this too. When you want to get off the darkest ground, but gravity pulls you straight down. When you want to get off the darkest ground, but gravity pulls you straight down. Clear When you want to get off that darkest ground, but gravity pulls you straight down. Earth from a bird's eye view. You should grow feathers and see this too. When you want to get off the darkest ground, but gravity pulls you straight down. When you want to get off the darkest ground,
drowning, I've been floating away. Every other dollar that I got in bed, I probably went and it away. I ain't feeling okay, I ain't liking it, babe. I don't even wanna talk, I'm just smoking my haze. I've been stuck in my ways, I've been stuck here for days. I've been staring at the clock as the radio plays. I've been rolling another, I'm stuck in my seat for the whole control of my speech. Yeah, I've been trying to get off this couch for a minute and a whole week. No kidding, I'm skinny, I cannot eat. Got a million things that depend on me. Yeah, every friend in my family, from a girl, every fan I meet myself. I'm too on till I'm too off. Come down, make new thoughts, like jumping off of that rooftop. Oh my devil, when I do not to make moves based on my mood drops. Like who frost, like who frost. It's yo, steadily killing me, running my brain full of shame. I don't wanna lose it. I'm full of stage, trying to find my pain. There's something coming out of that rain. My tape really not tame. I'ma never slow down. I'ma never behave. Stuck inside this prison, inside this cage. It's taking over. Yeah, I'm a slave. Slave for you. Ripping harder, more less. Never stop, no rest. Till the stress is breath in my chest. Till it's diamonds wrapping my neck. Progress to a god from a god. Mess, whole place, more tests. More blessed. Dug deep down, trying to find my best. Find a beast and a killer conquest. I'm next. I'm too on till I'm too off. Come down, make new thoughts. Like jumping off of that rooftop. Oh my devil, when I do enough to make moves based on my mood drops. Like who frost, like who frost. It's yo, steadily killing me, running my brain full of shame. I don't wanna lose it. I'm full of stage, trying to find my pain. There's something coming out of that rain. My tape really not tame. I'ma never slow down. I'ma never behave. Stuck inside this prison, inside this cage. It's taking over.
No point in blaming you, you did not know. Oh. I thought you were the one for me, that's why I gave you everything. Held you close by the stormy seas, oh you meant the world to me. I gave you everything, held you close by the stormy seas. Oh, you meant the world to me.
I got a premonition, I'm dreaming you and I. All my darkest fears are coming outside. We got a billion races, we got this melody, and you can trust me, baby, we got everything. Call me whenever you feel alone, babe. And when you need to cry, I'll be by your side. Call me whenever you need someone, babe. And when you need to escape from 1,000 fires, I'm gonna kiss you wherever you are, and I'm gonna miss you, I will never lie. Call me whenever you need someone, babe. We're running in the jungle of love. Jungle of love. To my conditions, I got you on my mind. You were stuck in my head and I don't know why. We got a billion races, we got this melody, and you can trust me, baby, we got everything. Call me whenever you feel alone, babe. And when you need to cry, I'll be by your side. Call me whenever you need someone, babe. And when you need to escape from 1,000 fires, I'm gonna kiss you wherever you are, and I'm gonna miss you, I will never lie. Call me whenever you need someone, babe. We're running in the jungle of love. Jungle of love.
Oh no, that is what they all say when they see me pouring some wine. Oh, then gets empty again. Better fill it out before I go. Cause I'm nothing and feeling it, touch me and being it. See what I see in it, I'm typical. Messing around with it, mix it up, go with it, fuck with it, flow with it, let it all go. Oh Lord, think you know what I'm like, but you don't fall, you lose control. Bittersweet melody when I dance. you don't. It is me you adore. How does it feel to breathe when you're dead? They've never seen you out of your bed. Cut to the bone, it's broken up. How sad. How does it feel to breathe when you're dead? They've never seen you out of your bed. Cut to the bone, it's broken up. Now come alive with me and quit the jealousy. I know you're bored, I know it's boring me. Now come alive, baby, get out the grave with me. I know you're bored. How does it feel to breathe when you're dead? They've never seen you out of your bed. Cut to the bone, it's broken up. How sad. How does it feel to breathe when you're dead? They've never seen you out of your bed. Cut to the bone, it's broken up. How does it feel to breathe when you're dead? They've never seen you out of your bed. Cut to the bone, it's broken up. How sad.
Somehow I woke up out in Beverly, fucked up, smelling like that bourbon. And I end up alone. I'm not certain. Yeah, the girls impolite in the club every night. That's how it goes when you Hollywood perfect. Hollywood perfect. That's how it goes when you Hollywood perfect. Hollywood perfect. Ain't got no place to call my own. Feels like I'm better off alone. So sad inside and hopeless. These Hollywood hoes never notice. Can't get back on. I miss you. Can't get back on. I miss you. Somehow I woke up out in Beverly, fucked up, smelling like that bourbon. And I end up alone. I'm not certain. Yeah, the girls impolite in the club every night. That's how it goes when you Hollywood perfect. Hollywood perfect. That's how it goes when you Hollywood perfect. Somehow I woke up out in Beverly, fucked up, smelling like that bourbon. But I end up alone, I'm not certain. The girls impolite in the club every night. Somehow I woke up out in Beverly, fucked up, smelling like that bourbon. How'd I end up alone? I'm not certain. Girls impolite in the club every night. That's how it goes when you're Hollywood perfect. Hollywood perfect. Hollywood perfect. Hollywood perfect. That's how it goes when you Hollywood perfect.
Who alive can't put me in a box. I redefine any definition you got. I am the tank, I'm making steps to the top. The flames, I whip it up, you just gotta hand me the rock. Take a seat, you cannot stand it. All I know, the flow harder than a Scotch
what's funny. Don't try to study me, you cannot manage. This ain't what you want, bitch, I'm a fucking phenomenon. This ain't what you want, bitch, I'm a fucking phenomenon.
Everybody, what is up? Let me just change the screens and then we can get started. Let me remove BRB, you can see the display. Why do I hear myself? That's very, very interesting. How do I check? Okay, there we go. Let me screen open up, blah, blah, blah. All right. So, yep, I have to reply to this guy, then I am free. Okay, so I might need to do a little Discord call now. What the hell? Okay, just give me 5 minutes.
Hi, Seshu. How are you? Good, good. I mean, crazy busy. You saw my server, right? A lot of workers and just crazy stuff. Yeah, but every single day I wake up, like, I'm scared of touching the phone because, like, the bot is, like, gone. Like, every day there's something wrong with the bot, and something has to be done about the bot, you know? But it helps me with managing the work a lot, so I really appreciate it. So I feel like after we figure out like every day to make sure that the total hours of the worker to be equal to the total hours of the customers, we need to. I want you to add a different function into the bot, and I want you to tell me how much it costs. Okay. So right now, I want each end embed to have like a ticket number, right? Like see, this is session number 10, session number 11, your ticket number, so that in the Excel sheet, when I send the bill to the customer, they can. So, like for example, today, 24th of September, right? They did this much in the hour, and then in the customer sheet,
Alright, humans. Alright, I'm back. So initially I forgot to mute the desktop audio, so that was a big fail. But anyways, we have 0 viewers. What the hell? The stream's audio bitrate is 0. Weak. So let me think what I was supposed to do today. Learning about algorithms. I'm glad I started a live stream. Otherwise, I would be asleep now or something. Let's start.
A lot of times you'll learn about.
Wait, this thing is free, so I think it is fine. I will not get a copyright strike for watching this, right? Right. Wait, github.io. The last algorithm class you need. Alright, let's check it out, man. Let's hope this will be the last one. So this is 9 hours and 20 minutes. Sounds like 9 days, and then we are good. Let's check it out.
Algorithms like Merkle trees, and you're like, wow, this is incredible. But then you're never going to be. All right.
What?
You know, the phrase kind of old-fashioned to interview with algorithms, right? That's kind of like the Twitter momentum right now. Is that if you do whiteboarding interview, the company's stupid. You know, whatever Twitter says. I did bad Twitter impersonations. Or you don't actually use any of them on the job. Well, the reality is that, sure, maybe algorithms aren't the best way to interview, and sure, maybe you don't use a lot of them on the job constantly, but the reality is that there is a secret handshake to get into a very good paying job. Learn the handshake, right? Like, why fight the system when it's just available and it's free online to go learn, and you get an opportunity right now to learn. So I always thought that was kind of like a strange argument. So here we go. So here's the big question I want to ask you.
Sounds
Is
like
that an array? What's used here?
Sounds
For those
like
that I assume everybody here is familiar with TypeScript. I chose TypeScript intentionally because I want the broadest audience possible. Is that an array? Would everyone say that's an array?
Yes, sir.
Okay, great. Well, what if I told you that's not an array?
That will
Would you
be.
be shocked?
Maybe that is an object.
Because you're
Maybe
like,
that's
wow,
an
my life's
object.
a lie. Also, extremely old meme. Yes, I get it's a very old meme, and yes, your life may or may not have been a lie. Remember, arrays are the simplest data structure. You should be able to know if you're looking at an array or not, right? They're the most fundamental basic data structure. Well, let's find out. Next, we'll also cover time and space complexity. There's not going to be any proofs. I will do one small solving of an equation. Nothing really
Sounds
large,
like
but we're
math,
just going
man.
to try to keep it pretty simple because for the most part, in the professional world, you don't do a lot of time-space breakdown. You really only do it during an interview, and you don't even do best, average, and worst case. You just do worst case. Like, what's the running time? Well, actually, if you give this input, you don't even do that. You're just like, it's this. And why TypeScript? I chose it because it's the most beginner-friendly language, even though it's object. So if you just give me a Pojo, a plain old JavaScript object, with foobar as the properties, I can't distinguish two of them from each other. So you can't even create a map in actual JavaScript. So there is this kind of uniqueness with JavaScript that makes it kind of a terrible language for this. It also doesn't have arrays in the traditional sense. There's a lot of unique things about it. So,
Okay.
by the way, if you're also interested in real languages such as Rust, we just released this course, I think, yesterday. I programmed in TypeScript and in Go. Graham over there saw this, and in Rust, and I built the same application at the same time in all three languages, helped me learn a different language.
Okay.
Who am I? I am the CEO of the startup. Please try harder. I do a YouTube channel. I'm almost at 100,000 subs. That means I get a little plaque, which means I get to lick the plaque. Very excited about that. I stream a lot of live coding. That's a lot of fun. And I poop post on the internet. That's for you, production team. And there you go. That's a great one. No one can actually mention it. Anyway, so I hope you guys are ready to get started. I intentionally tried to make this introduction as short as possible because
Okay.
the main contents that, or the topic semester class, a little bit of the fourth semester class, and my second semester class as short as possible because the main contents that, or the topic we're covering is fairly large. I want you to get the most out of this. So there we go. And one last note, when I was at university, I did a this two-day course is approximately the second semester class, a little bit of the fourth semester class. And my second semester class met 3 times a week for 1 hour. It's expected, for 15 weeks, you're expected to do 3 hours of study for every 1 hour, or 4 hours of study for every 1 hour of class time, plus a 1 hour lab once a week, which is 5 hours of preparing. So that's equivalent to 225 hours over the course of 15 weeks. And we're going to try to do all that in 16 hours, plus lunch breaks, plus bathroom breaks. Are two books that I've bought minimum. It's going to take some of your effort outside of this to really understand a lot of these things. Here you go. Here are two books that I've bought minimum. Of these two books, I've bought at least 4 copies of them combined. So I may or may not have lost them over the years. The first one is extremely academic. This Introduction to Algorithms. It's very, very academic. It's going to go over proofs, but it is by far the most complete book I've read on algorithms. Anyone who's in the chat who's mildly familiar with algorithms or went to some sort of school will probably guess the book, guess what's on the cover of the tree book. The second one is, I named it this way because I thought it was funny for programmers who don't know data structures and would like to do other things well too. That one is, it's a Zoolander reference for those who don't know, but that one right there is more of a very simple one. This course will cover about maybe 75% of the book, and then it deviates in various areas, but that one's a much more beginner-friendly one. The proofs are much smaller, if there is really any proofs to it. The topics are a lot lighter. They don't cover nearly as much in trees. They do a little bit of graphs, right? So it's a much nice.
Okay.
We're gonna first tackle Big O, because I do feel like Big O is kind of that one thing that if you don't know it, it just means I'm gonna be saying a bunch of nonsense up here, and it just kind of sucks because then we keep talking about it and you don't know what it is. So Big O, the easiest way to put it is that it categorizes your algorithm on time or memory based on the input. It's not meant to be an exact measurement. So if someone's not going to say, oh, your algorithm's going to take 450 CPU units. You're going to first say, well, what's the CPU unit? And second, how did you come up with that exact number? Instead, it's a generalized way for you to be able to understand how your algorithm will react as your input or the things you are using grow. And so if someone says, oh, this is O of n, what they mean is your algorithm is it grows linearly based on input. We'll go over some more. And so why do we use it? Well, it often helps us make decisions on why you should or should not use a specific data structure. You'll see as we do this that data structures progressively make these constraints to make them more and more performant. But if you use them incorrectly, they become massively, ill-performant, unperformant. I don't know what the opposite of performant is. Imperformant. There we go. So here, we're going to take a quick code example right here. For those who know Big O, this is a breeze. You know it immediately. So if you don't know Big O, this would actually be really hard. You wouldn't have a way to be able to kind of describe what is the running time of this code. You wouldn't actually have lingo. So hopefully we can do that. We can get this lingo going. To say it differently, Big O, as your input grows, how fast does your computation or memory grow? So that's the most important concept. Number one, growth is with respect to input. So just remember that, put that in your head. Obviously, in the real world, this is not a real trade-off in the sense that depending on the size of data you use, depending on how much memory you have to allocate, depending on the GC pressure, these things are not necessarily free trade-offs. You can't really trade time for memory because it takes time to create memory. So if you create a linear amount of memory, in some sense, your algorithm is bound by how much memory you create. So it's not necessarily for free. So let's go back to our example. So how does our program grow with respect to input? Well, I conveniently named it n intentionally, but notice that it is a string. So it has a length and has a series of characters associated with it. Strings are effectively arrayed, really, when you think about it. But anyways, so here we go. So if you look at the for loop, what you'll see is that the for loop has to execute the length of the string. That means if our string grows by 50%, how much slower is our function? 50%. It grows linearly. For every one more unit of string, there is one more loop that it has to do. So there you go. That is the simplest way to put it. And for those who did not see that, it's not very obvious. But for me, it's O. That's O of n. You can see it right away. So how can you tell? Simplest trick in all of it is just simply look for loops. Where do you loop over the input? If you see that, easiest way to kind of tell the Big O complexity of anything. All right. So when we look at this, you'll notice that I now put a new function, and we have a function that goes over and sums all the things that are happening here in the string, and then we do it again. What's the running time of this function? Anyone?
Bracket n into 2 most likely.
Okay, we got one O of n. Anything else? Because we do a sum and then we do a sum again. I was really hoping, can someone just say 2 of n? 2 of n. Hey, you know what? Or O of 2 of n. Oh, yeah, you're right. What's the running time? Right? No, it's not that. It's actually not that at all. Second most important concept is you always drop constants. The reason why is, here's a very good example of why you don't care about constants. Though practically speaking, constants are extremely important. Theoretically, they're not important. If you had something that grew at 10n versus n squared, you'd clearly see as we get down here, n squared just gets massively larger. It grows disproportionately fast in comparison to no matter what constant is in front of the linear O of n. So yeah, so that is why constants aren't necessarily important, because again, we're not trying to get exact time. We're not trying to get, this is how many units of CPU you need to use. It's how does it grow? If I'm going to give this thing 10,000 as n, is it going to halt my computer, or am I going to be able to do it fast? Is it going to be instant? I need to kind of just generally know where it's going to be. Okay. And so that's kind of the heart of Big O, if you will. All right. And I've talked about this, right? Practical versus theoretical. Yes, O of n is faster than O of n squared. But just like in sorting algorithms, often it will use insertion sort for smaller subsets of data, because insertion sort, though slower in theoretical terms because it's n squared, is actually faster than, say, quicksort, which is log of n, when it comes to small data sets. Because practically speaking, sometimes things that are n squared are faster than n, right? Because your n is sufficiently small and the constant that is dropped is larger enough that it actually makes real impact. All right, so let's do another example right here. We're going to go over the entire length of the string, and if we happen to run into a capital E, we are going to return whatever we have at that moment. And so what is the running time of this algorithm?
It should not be ON. It should be...
O of n would be correct. Good job, chat. The reason why we do that is that often we consider worst case.
Oh.
And so when you're in interviews, you're going to pretty much exclusively describe worst case. And if you think about it, a string without a capital E, how much of the string are you going to go through? You're going to go through all of it. A string with a capital E at the end, or maybe 1 unit from the end, or 2 units from the end, you know, you're going to get big O of n minus 2. Well, that's just simply n. You drop all constants. There you go. It's always n, because it doesn't matter where that E is. Practically speaking, it could be in the middle, it could be at the end. And if it's 1/2 n, still, again, it's just n. So the 3 important concepts I want to drive for time and space complexity are these. Growth with respect to input. Constants are always dropped. Whenever you're pretty much doing in an interview, it's worst case scenario. Rarely are they going to ask you for best case or even average case. Now, there are some algorithms that it makes more sense to reason about the best case and the average case, and we will go through some of those today because they actually change, and there actually is a variety of runtimes for them. But at least whenever I've done interviewing, I have never once been asked for best or average, and I've conducted about 200 interviews, and I've been in about 50 interviews. I've never had it, so I just assume most people here aren't ever going to have it. So here's some common complexities you will see. You got right down here in the ones that you can't really see, there's actually 2 lines right here, which is O of 1, which means constant time. It doesn't matter how big the input is, it does the same set of operations every single time. It's instant, effectively. Now, that constant that's in front of the 1 can be a very large number, but it doesn't matter because it's the same constant no matter how big the input is. Then there's log of n. That's base 2 log, for those that forgot what log means. Don't worry, I failed it on my ACT. I'm sure we all forget it at some points, but we'll kind of go over it more. Log of n being the screen line. You can see it kind of grows linearly, even though this graph is rectangular, so it doesn't look very linear. Log of n log n, very common running time you'll see. N squared, you can see that it starts becoming kind of ridiculous. It grows pretty fast. And the last 2 are effectively algorithms that can't run on traditional computers. I don't know if it can run in the quantum realm, because quantum realm is practically magical as it is. So whatever realm that is, I don't know about that. But traditionally speaking, you can't solve the traveling salesman for like 12 cities. That is a algorithm that runs in the last 2 time range, right? It's just effectively impractical on a computer. It takes thousands of years. All right, so let's go over some more examples. Again, I said count the loops. So n squared, for every single character in the string, we're going to go over every single character in the string. That is like computing the area of a square, right? N by N. It's just a square we're going over. We're just going down each single line. You can think of it kind of like a graph that you're going over. So for every single character, we go over every single character. Same thing for cubes. For every single character, we go over every single character, every single character. We won't pretty much see any of these type of algorithms today, but that's like multiplying a matrix, right? If you just simply multiply a matrix together, two of them, you're going to get an n-cube-like algorithm because you have to do this every single time, right? And then you have to do that a bunch more times. It's very, very painful. N log n, we will see some n log n and some log n algorithms. Quicksort is one. It'll make more sense once you look at it, but effectively, I think about that a bunch more times. It's very, very painful n-cube-like algorithm because you have to do this every single time, right? And then you have to do that a bunch more times. It's very, very painful. N log n, we will see some n log n and some log n algorithms. Quicksort is one. It'll make more sense once you look at it, but effectively, how you think about it is that for every time you go over, you half the amount of space you need to search, but you need to search the whole space once for every time. So you go over n characters, then you half how much you need to do, and you go over n characters, you half how much you need to look at, and you just do that. That's kind of how I think about it. And then, of course, log n, you just half the amount of input you have to search, but you only need to look at 1 point at a time. And so it eventually goes down to 0. All right. And then we'll also see the craziest of all runtimes today once. I've only seen this in one problem once. I'm very excited about it. O of squirt of n. Yes, I do math dot square root as squirt. I think that's fantastic. But squirt of n is it's a very unique one. And I think it's actually, it does show a mind-blowing trick that you can make. The important part, right. So why it's so obviated? Of course, we don't need yet another big O explanation. I just wanted to make sure we're all on the same page.
What does obviated means now? Oh wait, that's not a website. To remove difficult problem or the need for something. Okay.
Because again, the algorithms in this course are the important part. It's not necessarily the big O. I'd rather have you have the technical understanding of algorithms than to be able to tell me the running time. The runtime, once you kind of get the trick, look for loops, okay, see how we're going over input, it's just easy after that. As long as you keep these 3 concepts in your head, both with respect to input, constants are dropped, consider worst case, you're going to do fine in an interview. As long as you kind of qualify, okay, here's where my loops theoretically are, we're good to go. One more note, there are other things that measure time complexity other than big O. Just people don't use it, right? There's theta, there's little omega, there's all these other ways, but big O is the upper bound. So effectively the least upper bound you can do. All right, space, the final frontier. We are not going to really...
Seems like Dog-san is angry. I wonder why.
Space growth, I will mention it from time to time. It's just less interesting. I've gotten it once or twice in an interview, but the reality is that people do this in React, which emotionally bruises me. And so when I see this, I just assume people don't care necessarily about space or time sometimes, and I care about it, but I can't do anything about it. Hopefully those that, I don't know. This may not be the popular way to do it anymore. React changes too fast for me to keep up with it. I don't really do a lot of front-end stuff. So anyways, before we go, questions. My favorite algorithm to implement is probably Quicksort, and I'll explain why. Because I think it's just super
Let me get some
neat.
water, man.
Practically speaking, I think a ring buffer.
All right, everybody, I am back.
It's just always is awesome. And then you can replace a ring buffer with an array list. You don't need first in, first out behavior. Right?
All right.
Everyone agree? By the end of the course, you will agree with me because then you'll understand what I'm saying here. In fact, by the end of today, you should be able to understand what we're talking about. Yep.
I don't know TypeScript, can I follow the course?
You should, if you don't know TypeScript, can you follow the course? Well, I chose TypeScript because the typing language is very straightforward. We're not going to do a ton of TypeScript. So if you know JavaScript, you know TypeScript, except for you'll see some foreign characters in some unique positions. But it's really the types that are important. And so I really want to make sure I can type out the types so you can see it. And I kind of created a nice little project in which we will all practice typing out algorithms together. And that one is going to be in TypeScript as well. And there's a reason why I chose that for just like the technical reasons of TypeScript as well.
All right, that's cool.
All right, so shockingly, we're going to do the first data structure. We're going to start with the data structure first, not an algorithm. You've already seen this data structure many times in your life. All right, so shockingly, we're going to do our first data structure. We're going to start off with the data structure first, not an algorithm. You've already seen this data structure many times in your life. Is everyone excited? All right, we got lots of smiles. I think I saw one here. It was just one here. All right, arrays. Yes, I know we're going to cover arrays first. You're probably saying, well, I know what arrays are. Well, you also said that that was an array, which is not an array, so we're going to do this. And so I'm glad this joke worked out because it wouldn't have been funny if I didn't. So if Kant's array isn't an array, well, what is it? Well, hopefully by the end of this section, we will be able to derive what it is. We'll be able to empirically look at it and say, oh, it's actually this data structure. JavaScript arrays are actually much more complicated than that. They do a lot of cool tricks underneath the hood, and I'm sure they morph algorithms depending on how you use them. If you have an array that uses huge numbers, I'm positive JavaScript, and I'm like, well, you did set one element at 1 billion. We're going to create 999,999,999 positions before it and put that into memory. I'm very sure that they're very smart, so they're not quite the data structure we'll point out. They do a lot of things, but I'm also positive they are this fundamental base you use as an array. All right, so let's jump with this. I'm going to go to the whiteboard, and then we're going to go to Node, and we're going to observe this. And the most fundamental kind of idea of an array here, I'm going to actually write this up here, and then I'll save these, and I'll put them on the website as well. An array. So the most fundamental idea of an array is that all it is a contiguous memory space. Contiguous meaning unbreaking memory space, in which contains a certain amount of bytes. Now, everything about a computer is just numbers. These are all zeros and they're all ones, right? That's all they are, is a bunch of these things. And how memory is interpreted is based on what you tell the compiler or whatever, like how to interpret it. And so when it sees a chunk of memory, and it goes, oh, well, these 4 bytes, I'm going to treat them as a singular number, right? This is actually going to be a 32-bit number. That is the compiler telling, or that is going to be your program just understanding this piece of memory in a very specific way. Just because it's contiguous, just because it's all one piece of memory doesn't mean that it has any specific meaning until you give it meaning. So an array is effectively just a big, long version of this where you have 0 or more pieces of memory that are understood as a single byte in a row. So imagine if you did, so in a more traditional language, you could do something like this. I have an int array of 3, meaning I want 3 ints in contiguous space, unbreakable, like for me to be able to use. And so now you can lock that space by simply providing it. Say we call this thing A. I think I went to the edge of my screen where I can't actually put anything in there. Let's say we did that. There we go. And if you wanted to walk that, if you did A0, what you're really telling the computer to do is, hey, go to the memory address of A, then add in the offset of 0 multiplied by how big my type is. Because if your type is 32 bits or 4 bytes, index 1 has to be 4 bytes into the array or into the memory space, and that's kind of what creates an actual array. And so for people to kind of see that and understand the fundamental operation, I think it's really, really good because it helps kind of put yourself into the mentality of a computer. Because when you access these big, long pieces of memory, to you it's very abstracted away. It's just like something that holds, it's like a slot. But underneath the hood, it's going to be contiguous, it's going to be just zeros and ones, and something has to understand that and make it into the type you think it is. And so that's effectively all an array is a simple contiguous memory space. And so I wanted to just put that out there, just so it feels like we are talking about the exact same thing. And I can kind of actually show you that. So I'm going to jump into Node for a second here, and we're going to create something called an array buffer. So Node does have something like an array. so I go like this, const A equals new array buffer 6. So now when I type this out, you can see it's just a series of zeros. There we go. So I have this beautiful series of zeros. And I want to interpret those zeros in a specific way. So I can go like this. A8 equals a new uint8 array. So I'm going to take them as unsigned 8-bit numbers. That means a number between 0 and 255. And I'm going to pass in A. So now I have a view into this. And I can do something like this. A8 0 equals 45. So now when I print out A, you'll notice I've actually changed a piece of that data. When I do a simple, so let's go by 2, I set 2. When I do it again, you'll notice that I set the first byte, skip 1, set the second byte. Kind of interesting, right?
Yeah.
But now I can do something like this. Const A16 equals new uint 16 array A. And now we'll print out the contents of the array. As you can see, nothing has changed. If we use our new uint16 array and set the second index, remember, we use the width, so this one should be further out. It should be the last 2 bytes. And set it to 4545, which is a pretty large number. So now when I print it out, you'll notice something. I specified the first one in decimal, and we got a value of 2D. Specified the second one in hexadecimal, got 4545. But what you'll notice is that I said position 2, and look at where it set it.
Last 2.
Like it set it on the what is it, the 5th and 6th byte. Now that might be a bit confusing, but what I just did is I took a contiguous memory space and I interpreted it in 2 different ways. I first said, oh look, I'm going to look at this as 8-bit units, and I can walk them in 8-bit units. And I said, okay, let's look at them in 16-bit units, and I can walk them 16 bits at a time. Very, very different, and that's effectively what is going on underneath the hood. This is fundamentally what an array is. I'm walking these positions. And I know this might be a bit confusing if you've never seen any of these things. This is very, very confusing. Most of the course isn't going to deal with this. I just wanted to make sure that when I say array, this is more of what I'm referring to. When I say list, I'm not referring to that. And I wanted to make it as abundantly clear as possible so that way we have the same language together as we go forward. All right.
So you set A16 to that, and now A got changed. I don't know.
All right, so yeah, let me walk through. For those that don't understand what happened, so an array buffer is a contiguous piece of memory you can create in JavaScript. Then you can create views into this data. And so one view I created right here was an 8-bit array. That means every single time I increase the offset into it, it's going to take the width of that type, which is 8 bits, multiply it by the offset that I give it, and then edit or get that value. So when I say set position 0, it goes, okay, I'm array buffer A. I'm going to go offset times 8 and grab that piece of memory. Then I do it again with 2. Okay, I'm going to do 2. I'm going to go over that amount, 16 bits. Then I'm going to grab from the effectively the 17th through the 20, or the 16th through the 23rd bit. I'm going to grab that for a byte. Chris grabs the second byte index, that is, and grabs that out or sets that in. But then I create the exact same piece of memory, A. But this time, I set it as a 16-bit. So I completely changed the value that I'm looking at. Right? Those are 2 very different values. In fact, if I were to store the same value due to my computer, what is something called endianness, when I store this value, it will be a bit confusing when you look at it because of how computers interpret it. Look at where it put that 45. It put it in the most significant position, probably not where you thought it was going to put it, but that's because I've now interpreted this memory space differently than 8 bits. I'm doing it as 16 bits. Endianness, we won't talk about endianness.
So the when you set up the array, as you know, that when you told us that this is an array, the reason it's not defined.
It's not that it's not defined. We will go over it, but there's operations that you can perform on an array that you cannot perform with the JavaScript capabilities. And we'll see why. Well, I mean, technically you can, but we'll go over that. Effectively asking, is it because we didn't set anything on here when creating the array? No, that's not it. It's fundamentally not an array. In some sense, it's fundamentally down at the most basic unit is an array, but at the same time, it's not an array. And we can talk about why. All right, so let's talk about some operations you can do. I've already pretty much covered everything about getting data at a specific index, right? It takes the width of the type, multiplies it by the offset, puts it at the memory address, and you go in and grab that. Now, that may not be exactly how things happen, but that's the simplest way to understand it when it comes to how arrays work.
Okay.
So how does insertion at a specific index work with an array? Well, the thing is that with arrays, there are no like magicalness. So when you insert something, it doesn't necessarily insert it, it overwrites it, right? So it's just going to set that value. You do not get to grow your array in more memory, because what happened if right after that, you have the user's name, right? So if you grow this, what's going to happen to poor Fred? Well, that's F's in the chat for Fred, right? It is completely gone. And so we cannot grow an array just simply. That is why these data structures exist, is because it makes life easier for you, because it would be really annoying if you constantly had to reallocate everything every time you wanted to grow it. That's why you'll notice things like capacity in a lot of other languages that aren't JavaScript. You'll see these kind of things because what they're doing is they're trying to make an optimized way for you to be able to use the memory without reallocations and all that. Let's see. And so that's just insertion, right? It just overwrites it. And of course, insertion again is you just go to A's memory address, if you will. You add in the width of the type, which is usually specified in bytes. So it'd be like, a 32-bit integer would actually be 4, right? It wouldn't be 32 bits, multiplied by the offset, and then we can write it in. And deletion, exact same thing, but deletion's kind of confusing. You don't delete something out of contiguous memory. I could set it to 0, right? That would be kind of deleting, right? It's how your program interprets it. And so you will have, if you're actually using raw arrays and you're actually doing something, say in C, you have to be able to tell yourself when you've deleted this piece of memory. You can't just simply be like, oh, it's not anything anymore. That's like null. That's where null comes around. Null, of course, means zero value. Just like, hey, it's not something. And it's just a named way for us to understand that there's not something in this very something spot. And so deletion works the exact same way. You get the offset, set some sort of sentinel value, 0 usually being it. And there you go. You now have yourself deletion, getting, and inserting. Now, I did talk about this big O business. So let's talk about it. What is the big O of being able to get a value out of an array? Now remember, this is our equation we run. So if our array is size 3, does getting at a specific index grow with respect to input? If I give 7 as my index, if I give 100 as my index, does any of this change right here?
I'm seeing O of 1, O of 2 then, constant time, O of...
I love the fact that I just heard O of 2 event. Thank you for the call.
Man. All right, I'm back.
Back to the previous joke. Really appreciate that. Again, Padme, too bad, right? No, what it is, of course, it's constant time. Because you'll notice that nothing in here goes over the entire array, right? We don't have to walk to that position. We know the width of our type. We know the offset. Multiply them together, get to that position, read out the value. That would be, again, same thing with insertion, same thing with deletion, which deletion is really just insertion.
That
right?
makes sense,
They're
yeah.
all O of 1 because they're all an instant operation in the sense that no matter how big the index is, we don't do anything extra. So that is a constant time. I really wanted to highlight what constant time looks like because constant time can be a bit confusing the first time you see it. It doesn't mean we literally only do one thing. It just means we do a constant amount of things no matter what the input is. It does not grow with input at all. All right, there we go. Here we go, just kind of like just a bit of a summary, right? Fixed size, contiguous memory chunks. You cannot grow it. There is no insert at. There's no push or pop. Doesn't mean you can't write all those things. And the data structures we're going to create will actually use arrays underneath the hood often as ways to, grow and all that. They'll have to implement growing. You'll have to implement pushing. You'll have to implement popping inside of our algorithms. But for now, that is an array. They'll have to implement growing. You'll have to implement pushing. You'll have to implement popping inside of our algorithms. But for now, that is an array. questions on what we've covered up to this point on what arrays are?
So you're saying there is no insert or push or pop in array.
The question was, there is no insert or push or pop in arrays. Technically not. Not if it's a static array or a traditional array. There is no methods on it. In fact, in some of the older languages, there's not even .length, right? You have to pass the length as well as the pointer to the beginning of your array and just say, hey, here's my type, here's where it starts, here's how many you have. That's why when you look at any C program, the entry point is an array of strings and how many strings there are, right? Like it has to tell you how to interpret these pieces of data.
If an array doesn't grow, does its memory and size and memory allocation have to be specified at initialization of the array?
If you use Rust and you try to use an array, you'll realize right away that you have to put in a size. Like it has to be a specified size. And often you'll see this all over the place that you have to like tell it its size, and that's the size that's created. Now it can be a variable still, right? You can still create an array within the size in a lot of these languages, but it still has to be a specified size. There are also like compile time arrays.
My bad.
It's a 3, it's always 3, it's always going to be a 3. Right? There's kind of these different styles, but nonetheless, an array has to have the size as part of its allocation. You can't grow it, you can reallocate, meaning you're going to have to create a new array, take your old array, write it into the new one. You now have a bigger array, you now have more room. But nonetheless, it is these fixed sizes. So the question was, when you're creating an array in JavaScript, are you creating something that has an array underneath the hood? In some sense, yes, you are definitely creating. There is an array. There is a literal array at some point. There is a memory buffer at some point underneath the hood, but we don't see it that way in JavaScript. And you also don't see it in Java. Java has the exact same data structure that they use. Obviously, JavaScript begin. There's a bunch of conditions that are part of your array that make it actually a lot more tricky to simply do. I'm sure they have a turn it into a map once you have too many items, or once you have too sparse of an array. I'm sure they have a lot of algorithms that make it 10 times more complicated than it is, but for the most part, it isn't. It operates like an array. I don't want to give away. Yeah. One more question.
I guess how big is the array that it's sketching?
So that is part of optimizing. So like in Rust, if I'm not mistaken, if you create a new vector, it's going to create effectively a memory buffer with the size 5 underneath. And so as you push pop, it has 5 units for you to be able to play in. Now, is that efficient? Well, that's the problem. How big do you need to create your underlying buffer to be able to effectively use that space without having to reallocate too much, or without not using it, right? We could all create 10,000 units and be like, hey, look, we'll never have to reallocate again. But if 10,000 units are big units, you're going to use a lot of memory just to have that in there. So it's a game people play. We'll go over these. It'll make a lot more sense once we go over the data structures that are used.
All right. It is
So
going
we
good
are
so
now
far.
going to jump into the A of algorithms. We have defined our first kind of data type. We are going to have that. So again, JavaScript doesn't really have arrays in the sense that we want to have arrays. So I will treat a bracket like an array. It will have a .length property, and just to make it easy, I won't go full CNF here requiring the length to be passed around and all that. But we'll just treat it as if it only has one thing, .length. So as we program, we practice keeping it a certain size and using it in a specific way. I think it's a lot better to do it that way. It just is a good way to practice these algorithms. All right. So one big thing we're going to be doing here is that we're going to be visualizing all the problems first. We're going to be discussing it with circles and arrows, boxes and arrows, and then we're going to program it. We're going to do a lot of data structures if possible. It's definitely a core competency. If you can get really good at this, visualizing, creating your problems first on a whiteboard, and then being able to translate abstraction into concrete, it's going to follow you for the rest of your life. It's an extremely good skill to have, and at this point, often I can just think about it in my head in these terms, and I can just write out a program without doing the intermediate step, and it's a great skill to have, right? So first, we're going to start with search, because search is by far something that you do often, right? I think everybody here has had to find some sort of value out of some data structure, so let's just start with the simplest form of search, which is search on an array. And even more so, we're going to start with the even simplest version of search, which is a linear search. So again, the first thing we do space for this? I think I have space for this. Awesome. So if we have an array that's from 0 to n, and we want to find some sort of value, right? So we have some sort of function called search, in which takes in an array and a value b, and we want to see, is this in here? So the simplest form we can do is do a linear search. In other words, we go to 0 and say, hey, x0, are you v? And if it says, hey, I'm v, we're like, awesome, it's at position 0. Else, we'll do it again. x1, hey, are you v? Question mark? Oh, you are? Awesome. Here you go. Now, this may look very familiar because I bet who in here hasn't used index of? Want to guess what index of is probably doing underneath the hood? It's just walking linearly until it finds the thing. So we are literally in.
Wait, 0.00 milliseconds. I mean, that's probably normal, right? Let's see. Wait a second. That is not normal. Anyways, who cares?
Implementing, if you will, index of. It's the simplest form of any sort of search. Now, before we do that, I think, do I have it as notes right here? Yeah, what is the big O of this type of approach?
ON.
So, remember, growth is with respect to input, constants are dropped, worst case is usually what we're going to measure. So what is the possible worst case situation? So that's the first thing you should probably define in your head. What's the way that this thing fails? Well, just like in our first kind of example, we had E and all the way to double again that space. And it keeps growing equally with the array. So what type of running time is that?
Linear.
Say that again? O of n. All right, awesome. O of n. We say O of n. That's what it actually looks like when you draw O of n. What that simply means is that as your input grows, so does the time it takes equivalent or linearly. So if it grows by 10, you get 10 more cycles in this loop, if you will. It's the easiest way to look at it. And so, of course, I wanted to implement this because it's very, very simple. But not only is it very, very simple, I also wanted you to get this onto your machine if you wish to follow along. So we can execute these things one at a time. I created this little library to be able to just do a bunch of algorithms. And if you want to do them every day, it actually creates a way for you to be able to do them as much as you want. I made it for you, so it's a proper shill. There we go. So here we go.
Anyways, let me just clone this thing real quick. Yes, sir.
Grab this thing, go over to wherever you want to clone it out. Now we're going to get a whole bunch of stuff. So long as you executed yard install and yard generate, you should see all these. A lot of these are going to be data structures or algorithms that we are going to implement today. Yes, you do see min heap in here. There's a joke. It'll be great. But for now, let's start off. A lot of these are going to be data structures or algorithms that we are going to implement today. Yes, you do see min heap in here. There's a joke. It'll be great. But for now, let's start off with linear search. So we'll open up linear search. This should be a very simple one. I believe all of us can just kind of program this on first try, which we will hopefully first try all of our algorithms today. So here's the signature, of course, which is linear search. I do like using snake case. Now, I don't know what happened to me. I always hated snake case, and I love snake case. So if you don't like it, sorry. So there you go. Our signature, of course, is that we have a haystack, a bunch of numbers, and a needle that we're looking for, the number we're looking for, and we're just simply going to return out the Boolean if we did or didn't.
Okay, so give me a second, my human friends. I think I might have a problem here. github.com/ not that. Of course not found. Let's try this. Right click, copy the link. Oh wait, you guys can see my screen, my bad. Okay. The machine. Nice. I don't see it here for some reason. How do I refresh it? I wonder. But anyways, we are in. So I will just do yarn install npmi, and we have a message. Minus 100. What's that? I don't remember what's my power as well. I think it's either minus 2 point something or it is 2 point something. I don't know. Anyways, let's see what he was doing. Wait a second. Can you guys not see my screen? Yeah. Oh, this thing isn't passed. My apologies. I was scared.
Go over to wherever you want to clone it out, and let's just clone this thing out. There we go. I'm going to clone it onto my machine. Awesome. So I'm going to open up Vim. I'm going to go to scripts. I'm going to go to day one, and now we're going to get a whole bunch of stuff. So long as you executed yarn install and yarn generate, you should see all these.
Yarn generate. That's very interesting. Let's try it. Burn generate. That worked. Nice. So if I will go in
So a lot of open up Vim. I'm going to go to scripts.
scripts.
I'm going to go to day one.
Day one. I wish I could see that, but source day one.
And now we're going to get a whole bunch of stuff. So long as you've executed yarn install and yarn generate, you should see all these. A lot of these are going to be data structures or algorithms that we are going to implement today. Yes, you do see min even here. There's a joke. It'll be great. But for now, let's start off with linear search. So we'll open up linear search. This should be a very simple one. I believe all of us can just kind of program this on first try, which we will hopefully first try all of our algorithms today. So here's the signature, of course, which is linear search. I do like using Snake-Case. Now, I don't know what happened to me. I always hated Snake-Case, and I love Snake-Case. So if you don't like it, sorry. So there you go. Our signature, of course, is that we have a haystack, a bunch of numbers, and a needle that we're looking for, the number we're looking for. And we're just simply going to return out the Boolean if we did or did not find the number. All right, so let's just implement that really quickly. We're going to do a classic for loop, right? And I has to be less than, of course, the haystack. There we go. And if haystack I equals the needle, well, guess what? We can return true. I normally do not return in the middle of a for loop, but for algorithms, I'm totally willing to make concessions on good programming techniques. So there you go. As simple as that. If we see it, we return true. If we don't, we return false. The simplest form of search that we're going to do. In fact, it's the simplest algorithm we're going to do today. To test if you've done it correctly, what we're going to do is we'll run this npx jest and then just partially type in the name of the algorithm. So npx jest linear. This should just run jest with a filter of linear. If you've successfully done it, it'll give you green. Fantastic. You can also just return true the first time it executes and false the second time. And if you can keep state between the two tests, you will also win. So there you go. I mean, don't do that. Actually program. But there you go. This is as simple as it gets. All right. And assuming everyone was able to do that.
Yes, sir.
So I really just wanted to make sure everyone had that piece of software on their machine, so I figured this was the easiest way to know that you have it. It should run. The reason why you don't use yarn test is that if you cut out the package and grep the test, you'll notice that I put all of them in there. And the reason why I did that, the reason why I do it this way, is that if you look at, you'll now see what's switched.
Anyways, I think I will do Bunex jest linear. Let's hope something will happen this time. That's very interesting. Very interesting. Doesn't work. Maybe I need to calm down and wait for it to load. Or I can just do burn install -g jest. And let's get back.
As currently called this thing. If you go to your Ligma config, you'll notice that you specify all the algorithms you want to generate, and then it generates them all. There you go. Pretty straightforward. So let's keep on going, because we kind of need to blaze a little bit faster than this. All right, so algorithm time. We're going to go.
So just failed to parse TypeScript config file. Just see, we are in there. Just.config.ts. That seems very fine to me. TS just node is required for TypeScript configuration. Oh, that's the problem. Burn install -g ts-node, and I hope it works. I really hope it works. Interesting. I see a log here. Now it is running stuff. So we have test folder for linear search list. Where is it? Linear search list. So the test is this equals to blah blah blah. Who cares? Let's get back
to our second algorithm. This one is a doozy, if you will. This is the most classic off by one problem I think there is in the universe. And of course, this is a basis for other algorithms or how people look at other algorithms. All right. So an important question you should always ask yourself when it comes to your data set, is it ordered? If your data set is ordered, you have new advantages you can take with that data. All right. So first, let's come up with the algorithm ourselves. Okay. So I want to kind of derive this in some sort of sense.
Okay.
So let's let's just go like that. We'll create a new one, plus it, and let's kind of derive this algorithm ourselves. So if you have an array, but it is ordered, we don't have to go here and say, hey, is x0 equal to the value we're looking for, right? We don't have to start in the first position. We don't have to go to the second position because we can make some set of optimization, right? So
I think it is binary search
comes
time.
to everybody's mind who is not familiar with this problem is that, well, you know what we could do is we could say jump 10% of n, right? I could jump 10% of n and say, hey, xi, are you equal to my value? Oh, you're not? Then I'll jump 10% more. Hey, xi, are you equal to my value? Oh, you're not, but you're now officially larger than me. Well, I better walk back 10% and then linear search my way through that, right? Because that means the value is somewhere between the previous one and my current one. You can make some kind of guesses here. Now, this is why this type of style of algorithm kind of breaks down, which is, first, let's ask ourselves, what is the worst possible case of this algorithm?
It is at the very... It is second
Well, the
last.
worst possible case is we jump by 10%. We're still larger than the current value. We still need to keep jumping forward. We need to keep looking. We jump by 10% again. Still not there. We're still large. We're still larger. We're still larger. We go all the way to the end of the array. We're still larger, which means we have some portion of the very last bit of the array unsearched, approximately 10% of the last part of the array unsearched. Let's now walk through that last portion and look. It wasn't there at all. It was larger than every element in our array. We've totally failed. This sucks. So what's the running time of something like that? Well, the problem is we used n in our jumping, right? We jumped by 10% of n. So that means we're going to do 10.1s. We're effectively going to do, what is it? We're going to do, what is that? 10 operations of jumping. There you go, sorry. 10 operations of jumping plus 1.1 of n, right? So that's effectively what we're doing right here.
Yeah.
So if we denote that in big O, what is rule number 2 of big O?
To remove the 10.
Ignore constant. So bam and bam. So what is our running time right now?
N. Just same as linear search.
It's still n. Isn't that just emotionally defeating? This is still way more efficient. And if you can do something like this, obviously it's much better than linear searching, right? Practically speaking. But theoretically speaking, if your elements go from 100 to 1,000,000, your algorithm is going to run that much slower, right? Whatever that number is, I should have chosen a better one. 10,000 to 1,000,000, your algorithm is going to be 100x slower, even though it's still 10 times faster than your every single index. And so that is problematic. We didn't improve the algorithm, we just improved it practically speaking.
Okay.
So what happens if we can jump differently? So how can we jump differently? If it's not, well, then we can check only one half of the array. If it is the value, awesome. So let's just say that our value is larger than this value. What do? Well, if we
The
just
next,
simply linearly scan back this way, well, then what happens? Worst case, 1/2 of n. Well, then you can say, well, let's just do it one more time. We could half it again, right? Okay, so let's just half it again. So now we are only looking over half the space to 1/2 n. So we half it, we're at 1/4 of an n. And if it is larger or smaller, we could then scan. Well, again, what's the problem if you scan at any point? You drop the constant, it's just simply linear. So we can't do that. We can't scan. So what we could do instead, though, is we could, let's see, we could do another one of these xi equals b. Oh, it's not? Well, we could then half it again, right? So let's go here, here. We then half it again. We can go here. This is if we chose a really small number. And we can keep on halving it until either there's no half left to look at or we find our value. And so let's think about how that works. That means effectively we have an array of size n, right? Then we half it. So now we have a value space that we're looking at that is really 1/2 n. Then we half it again. So now we have a value is met. Or in other words, n over 2k equals 1, right? So let's do, this is the most mathy part of the whole course we're going to do. So let's do the classic multiply both sides. There we go. Or in other words, n equals 2k. And of course, for those that remember their logarithms, you can say log of 2, let's see, of n equals k, right? Log of base 2 of n equals k. Or in other words, our running time is log of n, right? Because until we get down to 1, we have to keep halving it. So we're going to half it a log of n amount of times. So practically speaking, if our array was 4,096 and we half it, we'll have 2,048. Then we'll have 1,024, 512, 256, 4,096. It is 12. How many steps do we do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? At that point, you don't technically count the first one. I counted wrong. So this would be the 12th position because that's the starting position. You didn't half that one to get there. You get the idea, though. There you go. So you do 12 halvings to get to 1. And so at that point, you would know whether or not the value is in the array. So the worst case situation is when the value is not in the array and you have to halve it over and over again to the end. You will do a log n amount of halving. So this type of searching is referred to as binary search. Does that make sense? Binary, either 1 or 0, right? There's only 2 possible states. Technically, I mean, in real sense, it's kind of like a trinary search because there is also, it is the value, you know, the happy case. But in this case, it's either it's this side or it's this side, right? You're always splitting it in half. You're always traversing down 1/2 of execution.
Okay.
So let's look at this. Blah, blah, blah. Oh, yeah. Another good little trick of Big O, by the way, is when you half the input at each step, it's either log n or n log of n, right? So just remember that. That's depending if you're scanning that input or not. We're not scanning. We're only looking at a value and then dividing it into half. Looking at a value, dividing it in half. We're not scanning anything. So that's usually a pretty good trick to think about. So this binary search, greatest algorithm ever. So now that we've kind of written it on a whiteboard, we could implement it. But first, what I'm going to do is I'm going to probably do it a little bit nicer this time. Let's try to do it and do it in a sense that makes it easier to translate to code. Right? So let's think about it more in kind of a pseudocode type sense. We know we're going to have the array. We know we're going to look on either side. We know we're going to do this, so let's do this, you know, a little bit better. So if we think about it, we could have a function that has search that takes in an array, and maybe it has a low and it has a high, right? This is the space in which you need to look into, right? That makes sense. And so what we could do is we could do a loop until some sort of condition happens, right? What would be a good condition that would happen? Does anyone have an idea? Yeah, exactly. When the low and the high effectively become each other, we are done, right? Because that means we've halved our space to the point where we can no longer have our space. So that's a good thing to kind of remember, conditions always. But let's just kind of walk over this in a more practical sense. So if we start here, what we need to do is we need to go from our low to our high and find the middle point. All right, so that's pretty easy. Let's just write some pseudocode. All right, midpoint
plus high minus low divided by 2. Low plus high minus low divided by 2. Interesting. So let's think about it. I will need to open my whiteboard as well. I have a cool array and I have like 1, 2, 3, 4, 5. Now this is 1, this is low, this is high. So let's say 0 plus 5, 0, 1, 2, 0 plus 4 divided by 2, that will be 2. So this is it. Then 0 plus 2 divided by that, 1. I think my system is right. Let me just verify this. And if mid is equal, okay, let me continue the video as well.
Right, that makes sense. We're getting the middle point. Because if we're starting from a middle position, we're going to need to make sure that we adjust where we're at. That's why we do the low plus. And we need to just
Mid is greater than
we get the midpoint with the offset. Awesome. We're good to go. So then we need the value.
Sorry, it's needle.
Right? So we can do something like array.
So if needle is bigger, then that means we have to change our left value. Left should be equals to mid. I will need to think about that. Let's think about it. So I check this value and our needle is bigger than that. That means it is in here, right? So I can just, yeah, let's just try it, man. We will find out if it's wrong or not. And otherwise we can just set right as that. Let me set else right is equals to that. Oh, sorry, it is end. Wait, why it is left and then end? It should be left and start. What the hell? Left and right. Sorry, it should be start and end or left or right, obviously. So most likely that should do the trick. And I don't know, we will find out. Let me just do binary. Let me just copy the name as well, just in case if that doesn't work. And let's get back to the video.
Midpoint, right? So we now have the value. All right, awesome. So what do we do in our three conditions? Does anyone know what the three conditions are? Condition 1.
So we are testing binary search list and compare binary. Let's be a bit more precise this time and see how it goes. Let's see how it goes.
Value is the thing we're looking for, right? I forgot to put this in.
Wait, did I miss anything? So we have the middle index. If the middle value is equals to, then we are saying true. If middle value is less, that means we should start from the middle index, right? Hopefully. So the test failed for 69. We do have 69 here. Let's see what must have happened. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11. So my boy must have started at what? Let me think about that. 11 plus 0, that's 5.5. So that's most likely 5. So it started at 5th index. 0, 1, 2, 3, 4, 5. It started here. This thing is greater. So right is equals to mid. Right is here. Now here it must have. Can I add some console logs? Let's see. Console.log mid comma haystack bracket mid comma needle and boom. Let's see how it goes. I wonder if I can actually see those console logs, but let's see. No console log this. Nani. Okay, let's try something else. So I will do bs dash list. I will give an haystack of this, and I want you to search for 69, and I want you to console log that as well. Now I would like to do burn, right click, copy relative path, paste, enter. What's the problem? Module not found. Oh, my apologies. It said false. And why is that? Wait, the condition is wrong. While left is greater than equals to right, it should work. But that's exactly opposite. While left is less than right, it should work. When they are... Oh, so that was the problem. I am really dumb. I didn't realize that my mistake was such a silly mistake. Because if left is less than that, that's fine. But if it is equals to or more, then we have to stop. Right. So this time, this better work. If it doesn't, I don't know what to do, man. We have a lot of console logs because, of course, my bad. But anyways, let's wait for the response. Or should I just remove these logs? They are kind of painful. Clear. Ban. Now let's get back.
We'll just call it N for needle.
Okay.
If value equals needle,
Mm-hmm.
well, we can, return true in this case. We'll just make it simple, right? We're going to just return true. We have found the value does exist. Here you go. We could return the index if we wanted to, which would just simply be that right there. Doesn't matter. All right. Or we have our value is actually larger than the midpoint, right? So what does that mean? We're looking at this position right here. What that means is our value is larger than this position, which means that it's larger than everything on this side, which means we simply need to only look on this side, right? That makes sense. So we will simply have to do something. We need to do something to be able to do that. And the easiest way to do it is just adjust our low, right? Our low should equal the midpoint plus 1. We don't need to consider the midpoint. We already know it's not the right value.
Oh, I see. That's why. I can just do mid plus 1, and here I can do mid minus 1, because I don't need to consider that value. Of course, my bad, my apologies.
So we just adjust our low end and put it right in front of where the midpoint is. Else, we can say high. We now need the else condition is that our value is actually lower than the current value, which means that we need to go on the lower side. So our high needs to equal our midpoint. Now remember, I usually, whenever I do things, for the most part, will do something that looks like low is always inclusive, high is always exclusive. Always have these things in your head, or else this plus 1 right here is going to just eat your lunch. You're always going to be off by 1. Things are always going to break down. Always come in with a plan, or else it destroys you. And that's pretty much the extent of the algorithm. Now all we need to do is just effectively come up with our exit condition of this loop. And we've done it, right? Right. So our exit condition can be as simple as this. Let's use the Lord's loop, a do while loop. I just like to throw those in there because they're funny. Anyways, so there we go. Do while. Low, oopsies. Low is less than high.
Yeah.
Right? We just keep on going until we finally come to a crossing point. Because once we come to a crossing point, we're done. We're going to always keep getting closer to each other right here. So we'll know that will eventually happen. And if we get here, we can simply return false. Doesn't make sense. If you were returning the index, you could do a sentinel value of -1. That's what it's called. It's called sentinel value. Pretty fun. I don't know why I always think about the matrix sentinels. I don't know why that makes that association, but it just does. So there you go. That is effectively the entirety of a pseudo-code version of binary search. Does this all make sense?
Yeah.
Normally, why? Oh, we got one question.
Yeah, shouldn't it be less than equal to high?
We don't want to do less than or equal to, because if you think about it, see, this is classic. This is an off by 1. This is another off by 1. What does this mean? It means that low is included, but high should not be included. So if we include 1, but we should exclude 1, what does that mean? It means we shouldn't use 1, right? Because it means that our pointers are actually behind each other, is what that really, really means. In other words, if we're at some position, we'll just call this thing, x high, we have a pointer that says, hey, I want to start here, and then our end pointing says, hey, don't cross this line. So it's like fundamentally a broken state. We don't want to go there. So that's how I always think of it. I just have to have my off by 1 really strong, or else I can it up. All right, so let's, now that we've done that, let's, well, actually, is there any questions?
This is all under question that the array is sorted, correct?
It's all under the assumption that the array is sorted. You can never do this on a non-assorted array. The reason, again, is when you come back up to this part, when you come to these two conditions, it has to be able to make the assumption that if I am larger than the current element, then the rest of that side of the array, the left-hand side, is all lower than me. I know that for a fact. Everything over here could be larger or lower than me. I don't know that yet. But it reduces your search space by half each time. You can make that single value thing. And so since we did that, let's do, of course, the greatest thing ever. Let's go over to our coding machine, go back to day one, and look for, binary search. Oh yeah, look at that. So now we can implement binary search right here, right now. So notice that we're given a haystack and a needle again. So, as all, oopsies, and a high, I'll just keep in the same naming convention as my pseudocode, path.floor, and we'll do low plus high minus low, divide by 2. I put that little note, don't forget to divide by 2, because when I programmed this, it took me like 3 minutes to realize I had a bug.
It is the same.
I forgot to divide by 2. Don't forget to divide by 2. It's very, very important. Const value, of course, is going to be haystack. And you're going to see this a lot in algorithms that they use single letter variables to denote everything. I'm just kind of following the pseudocode style, so that way it's a fairly easy direct translation from this into here. Normally, program with good names, but in this case, we're just going to keep it like that. All right, so if value is equivalent to the needle, we have found it, right? I'll take that down. You can reverse the condition, or we can just do an else statement. Let's do an else statement to make it simple. Now remember, what this means now is that our value is less than our needle, which means that we need to search on the higher side. Once it begin, drop the mid. You don't want to look at the midpoint again. It would be silly if you look at the midpoint again. Just having these conditions all in your brain, as long as I've done this all correct, we should be able to see this thing go first try. Okay, let me just make sure that I've actually done this correct. NPX, just binary. I'm actually supposed to see that quite yet. So let's pretend the man behind the curtain doesn't exist. Look at that, our binary search actually worked. It was first try. All right, there you go. So I don't think I put this in my presentation, but one of my first interviews at Google, they made me code binary search in Google Docs. It was terrible, and I had +1, -1 issues all over the place. I didn't come into it with a really clean idea of exactly what needed to happen. This algorithm is actually pretty simple, right? Like, that's not a hard amount of code to do. It's, it's really only, 7 lines of actual code. The rest is all spacing, or, it's like nothing, right? Initialization and spacing. So it's actually a pretty simple piece of code. It's just being able to focus on this and do this correctly. Do we have any questions?
Just a quick thing. In the program, I couldn't see the day one folder. Just see the test folder.
Oh, so it is. So what editor are you? So the question was, I can't see the day one folder. What's happening? What editor are you?
Visual Studio Code.
Okay, so code may is it hiding get ignored folders?
I'm not sure about it. Is that there in the Git?
It's a get ignored, so that way you can generate a lot of them and you don't have a huge amount of uncommit changes. So if you're using Visual Code, I don't use code. I didn't know that, but if it hides ignored folders, you're not going to be able to see day one. All right, so let's go on to the next part. So I'm going to actually give you an interview question that I had at my first job. This involves arrays. It's also a question that I happen to have in computational theory, which I thought was fantastic. Given 2 crystal balls that will break if dropped from a high enough distance, determine the exact spot in which they'll break in the most optimized way. Often you'll hear this something like, you're in a 100-story building and you have 2 crystal balls and you want to find out which floor do they break. So what's the most efficient way to do it in a 100-story building? This is just the generalized version of the exact same thing right here. So let's do the generalized version, because we're computer scientists. We generalize. We're not going to do the weak version. So let's discuss our options. We right now know of both linear and binary searching. So let's kind of talk about them and their associated time constraints. So if we have you can think of it like if we generalize this problem, really, when you really think about it, what it is, it's an array full of falses, right? That at some point it becomes true, and from there on out it's true, right? And we're trying to find where is this midpoint, or where is this point? It doesn't have to be mid. There's just a point in which no matter how much higher you go, your crystal ball breaks every single time. There's a point before where it doesn't break. Now, despite what Elon Musk says about the Cybertruck, if you drop this crystal ball over and over again, it won't break. I swear, that was a great joke. We just made that one up. I feel very good about that. All right, so what we want to do is find this in the most optimized way, right? And so if we start off at 0 and just linearly walk, yes, we will find it, correct? We will eventually get to true. It will break. But we are given a constraint, and we really didn't even use our constraint, which is we have 2 crystal balls. I apparently can't spell crystal. We have 2 of them, right? So therefore, we should be able to do something more efficient than that, right? Because if we linearly walk and find t, what is the runtime of the algorithm?
Where?
Imagine in your head what you're going to write. You're going to write a for loop, right? You're going to write a for loop over the space of the array, checking every single time. It's a loop. Trick, look for loops. There's a loop based on the input. Boom, linear, right? It's O of n. Very, very simple to see. Okay, we're like, whoa. We are so much smarter now. We already know something. This array is ordered, right? If we break it down in the most ordery kind of way, it's this, right? It's a bunch of zeros until it's a bunch of ones. We're so much easily do this. So again, we have an array. We jump to the middle. And we're like, hey, x of I, are you true? And it's like, yes. Oh no, what just happened there? Well, one of our 2 crystal balls just broke. And so therefore, what do we have to do with the remaining 1? We have to linearly walk from our last known good point until we hit a bad point. And if we walk 1/2 of n, what's the running time of that? Remember, rule 2. Yeah, drop the constants. Boom. Oh, dang it, I drew on the line. Bam. Oh, right, there you go. You've just dropped the constant, and it's back to n. So both of our searches suck, right? Like, neither of them work. I really wanted to work this one in here because specifically during the interview, the interviewer did not know the generalized answer, and when I just said it right away because I was so stoked, they said, well, that's not the answer. I said, it is the answer, and here's why. Oh, this is so exciting. So what do we have to do here? Well, the reality to the answer is this, is that we need to jump in such a way that isn't some portion of n that means we have to walk some portion of n. We need to be able to jump by a fundamentally different unit. Does that make sense? So normally what we did in binary is we'd cut the space in half. That makes it really, really efficient. But in this case, we're jumping, so we need to do something different. So here's what I propose. We jump the square root of n, the squirt of n, right? And so that means we're going to jump a square root amount of times until it breaks. And if it breaks, we have to walk backwards to our last known good point and find the point of breaking. If we walk back and we have to walk forward, how much are we going to walk forward at most?
Okay.
The square root of n. So what is the running time of having to do a square root of n plus a square root of n worst case? Right? Because we could have to do a square root of n jumps until we're off the board, back it up by square root of n, and walk square root of n. So what is the time of this?
Square root of n.
The square root of n. Look how fantastic that is. We actually did it. Now, you don't have to write it like this because, of course, you can rewrite that as the 2 square root of n, or of n. And so what do? You drop the 2. So we have just come up with a new running time that you probably will never see again, but this is a fantastic little exercise, which is we now have just broken down a search problem without doing a linear search. And I think that that's really kind of a cool thing. I love these type of tricks because often they'll expand my mind for me to be able to use this in other areas. If I see something that I can't use, say, a priority queue, which we'll talk about, and I need to be able to search in such a unique way, I have one more trick inside my bag. And it's always good to have one more trick inside the bag.
Why is this thing called front-end masters?
We'll implement it because it's so exciting. Oh, I really think it's exciting. I think this is a good exercise to go over. So again, open this up, search crystal balls. There we go. And so I'm going to pass in the breaks array, Boolean, and you're going to return back out the index into this array. So remember, just like our algorithm, we want to jump by the square root of n. And so how do we do that? Well, it's pretty straightforward. Const jump amount will equal math.squirt breaks length, right? But we can't really use just that because what's the square root of 3? I don't know, right? I'm not that smart, so therefore let's become that smart and let's use the floor unit. Let's assume that the array is big enough to have a square root. There we go, right? It's going to be effectively 1 for 3. There we go. So we now have our jump amount, the amount we want to jump. So what's the first step? We use our first crystal ball to see where does it break. So I'll go like this. Let I equals jump amount. Oh, we have a question.
Yeah, why suddenly square root and not having like before?
Okay, yes. So I did the worst case right here. So here's why having doesn't work. If you jump to your middle element and your ball breaks, what does that mean? Well, that means you only have 1 left. Therefore, you need to start from a last known good position, which is 0 in this case, and walk to half of n. Half of n, square root of n, means that we will at most walk square root of n. Or another way, does that make sense? It will make sense. For I has to be less than breaks length, I plus equals jump amount. There we go. And so now we just simply try to wait until we break. So if breaks I, then break. Oops, I just replaced that. There we go. Now we do exactly what we said. We find the point where it breaks. We walk back. We jump back square root of n. Then we walk forward square root of n. So
Okay.
equals jump amount. There we go. And now
Can you stop, please, man? Let me think. So we are running a loop, and it will be plus equals to the jump. Now, if let's see, if breaks bracket I, if this thing is true, then we break. And do we tell it that the ball is broken? I guess no. And then we are just going to run another loop that will start from previous jump. Let's do I is less than it should be less than I plus jump, to be honest. Okay, and it will be I plus plus. Let's see.
jumped back. So now we just simply need to walk forward.
Yeah.
So for let
Okay.
equals
Oh, that's also smart. We can do I plus j. He's smarter than me, man. He's so smart. So let j is equals to 0. J is less than the jump amount. And we will do j plus plus. And here we can do the if check with j plus I. What is it called?
And we'll go like this.
Breaks bracket j plus I.
Breaks length, just in case we walk off our board. We don't want to walk off our board.
Ooh.
And then we can just go plus plus j. Awesome. So now we're going to make sure we walk maximum a jump amount of steps. If breaks I, oops, I forgot one thing. Plus plus I, there we go. If we find the breaking point, there we go. We can literally just return I at this point, or we can return -1, right? There you go. That should be the answer. I always get so nervous about the run this.
Let's see. So if the thing breaks, if the current thing breaks, then what do we do? That means we are returning this index. Why are we doing that? Let's think about it. We will need to go on the whiteboard once more. So let's first of all let me do this. Blah blah blah. Boom. All right. So firstly, we have our first spot, right? So we have false. I think I should have used a copy instead of this tool, but fine. So let's say this is the case. We will start, we will go on the middle, that is this one. We will see, oh, this is one. Let's add one couple more of these so we have a better stuff. 1 2 3 4, 1 2 3 4. So we will start on this one. Let me use a different color now, red. So we will start on this one. We will see, oh, this is true, nice. Now I will need to move from this section. So the first one, which is true, is where the thing starts, and that's what we are supposed to return. Yeah, because we are supposed to return the index or the floor from which we are going to get the ball broken. Obviously.
I think that's all we have to type. Oh my goodness. It worked out again. So there we go. So here's the simple code, which again, we did it in the exact same steps. I'm going to jump over here. We first walk by the square root of n. Jumping I at this moment, which is the index in which it breaks, or we return -1. Hopefully that all makes sense. It's a pretty fun algorithm to kind of think of. I think it's a really kind of a challenging one too, because it just changes kind of how you view it. And you never know. I was asked this question. Maybe one day you guys will get asked this question. Likely not. Now that it's on the internet, completely ruined it.
What? Expected 7078 received 7000. So I'm returning I, but I should be returning I plus j because that's the index I'm checking. Am I dumb? Oh, I just copy pasted it. That's why. My bad.
But it's a fun one. So I've already said I've had this one. Oh, look at that. I even did the binary search in Google Docs. You know, it's shocking how many times you'll get asked to do binary search at Google. They just ask that question all the time. So, you know, come prepared. Be ready. All right. All right, so let's take a breath. You get it. Good pun. I think it's a great pun. I'm sure there is
okay.
a lot of questions. This is a great stopping point for any questions we can have at this moment.
Can we traversal cube root of n instead of square root of n?
We could travel a cube root. I wouldn't know how to. I wouldn't know what the running time of that would be though, because that means you'd also have to hop cube root of times, which is a higher amount of hopping.
Cube
right?
root is smaller than the square root of n, right?
Yeah, but that means you will need to jump more times.
I don't know. I don't actually know what that proof would look like and why it would be faster or slower. To me, it seems like it'd be slower.
What if we go more than square root? I'm just trying to figure out why we have chosen square root of n.
Square root of n? Well, the square root of n, it just is the only way we can change this from nonlinear running, right? Because if we use a binary search, we still run into a linear problem. If we jump by some portion of n, we're still running linear. So if we want to get sublinear, we cannot get to log. But if we just do a cube root, if we just do a root, then we get the maximum amount of jump, right? You get the maximum amount of distance with a still lower running time. As you increase, obviously, your root level, the closer you get to a linear run, right? Right. So if you do the quad root, then you get to the point where you're practically jumping by 1, right? Then you do the next root, you are definitely jumping by 1, if not by 0 at that point, right? It just like becomes nothing. So I think it quickly approaches n.
Wishing their college professor was you back in the day.
You know what? I still, if this ever gets back to Montana State University, Brock Lemires, best teacher ever. I model everything after him. He got Teacher of the Year award once. The man was writing on he did Carnot maps, he did digital logic, all that. He was writing on the board. He was so excited that when he tried to write, it launched out of his hand and made it all the way across the room. And I was sitting there like so engaged going, this is how I want all my professors to be, right? I want them to feel like they like what they're teaching. And I like what I'm teaching, so I don't want to. Also, of course, you have to do sorting. This cannot. So normally, when you look at algorithms books, it often starts at sorting. I think search is just a simpler concept to understand because it's very, very practical, whereas sorting often gets into this weird world. And so I wanted to start at search. But now we're going to do sorting. We are going to implement 2 sorting algorithms, but one of them
bubble and selection.
And so the first
okay, not quick sort. Okay.
Is bubble sort. Now normally it starts off with insertion sort, but the problem with insertion sort is the example always sucks. It's like a card deck. I still don't know how to sort cards. It's always a much harder sort to start with, which I'm surprised that we start that way, because bubble sort is not only really, really, really easy to visualize exactly what's happening, it's also 3 lines of code. It's an extremely simple algorithm. And my teacher once said, Ray Babcock, he once said, if an airplane was going down, stewardess, whoosh, kicks the curtain between first class and the economy, because I'd be traveling in economy. And she said, quickly, we need someone that can write a sorting algorithm or this plane will crash. You could write bubble sort under a plane crashing. It is that simple. And so we're going to go over it because I just feel like it is the greatest of all sorting algorithms. And so hopefully our plane does not crash, but let's get this sorting algorithm going. So let's talk about bubble sort. So the general definition, or the the quote-unquote mathy definition of a sorted array is simply this: any x sub I, meaning any
Is greater than
in the array,
or
is going to be less than or equal to any I plus 1, right? Does that make sense? This is true for
yeah, for
array.
ascending
That's
order,
how
yeah.
you know an array is sorted. So that's kind of like the mathy way of saying it. And so if we have an array that's not sorted, up as we go, I'm going to make it up and say, hey, am here. It's by rewalk this next progressively smaller.
Oh, so we are talking about that. Okay, my bad.
I'm not. All right. So then we go here. Hey, 3, am I larger than 7? I'm not. Hey, 7, are you larger than 4? You are. Well, fantastic. I'm going to
You
put 4
switch
here.
them.
We're going to put 7 here. A singular iteration. What happens in bubble sort?
That was quite easy, yeah.
The largest item is where in the array? It's at the end. So a singular iteration will always produce the largest item in the last spot. So this is actually kind of unique, right? So that means the next time we do the bubble sort,
You don't need to go to the last.
the Facebook as well. The next time we do bubble sort, it means we only have to go up 2, but not include the last position, because that is already sorted. We don't need to look there. So if I rewrite my array, 1, 3, 4, 2, 7, am I larger than you? Yes, I can. 3 to end with a 3 right here. 2, 1. I accidentally had my entire array sorted at this point, but we would keep running until we have only 1 position left. Because when you have 1 position left, is your array sorted? It's always sorted. An array of 1 element is always sorted. When we do it, right, we can do n, right? Does that make sense? We are now down to the very last element. Now, some people, they recognize this right away, right? This is a very familiar pattern that you should probably be familiar with. For those that don't know about this, there's a fun little story, and I'm going to say it. He was known as being a complete jerk. What he did it in about 10 seconds. He was completely done right away, went up and showed his teacher. His teacher said, no way, this is not true. And of course, it was true. And this is what he showed her. Add those 2 numbers. What do you have? 101. You can kind of tell where this is going. It's going to keep going until you have 50 and 51, right? Awesome. So really, if you think about it, you could just do 101 times 50 and you have the answer. But of course, we're computer scientists. We abstract this formula. So what do we do? Well, 101, and this was 100. I mean, to me, that's n plus 1, right? 50, well, you know what that looks like? That
N
looks like
divided by 2.
divided by 2. And if you run this and you do it, it works every single time. N times n plus 1 all over 2 just will tell you the sum of numbers between a range. And so the reason why I make that, or I say that story, is my math teacher told me that story, then went on to tell all the reasons why Gauss was such a jerk. But he was also extremely smart. And I think his middle name was Friedrich. Reverse that.
Why are we in that
now
much details?
2, 3. Let's break it all down, do the whole mathy thing. Well, first thing we can do is we can just drop constants, right? Because this is, of course, plus 1 n over 2 squared plus n, right? Well, in big O land, a thing you will do is drop non-significant values.
Well,
This,
yeah.
I believe the term is actually insignificant values. There we go. It's n squared. So that is the running time of this algorithm, is it's n squared. And the reason why you drop this is just imagine the input, even at 10,000, right? N's 10,000. N squared is like, I don't even know what that value would be, 100 million, I think, off the top of my head. But either way, that's a very large, it's so insignificant at some point, it just eventually goes to 0. As n goes up, insignificant polynomials go down. Same thing with n cubed versus n squared.
Okay.
you go. So that is the running time of bubble sort. And I'm very thankful that a third grader who makes me feel stupid actually was able to solve this for me, because now I have the value right here. And of course, you know what we can do? Well, we can implement this. And I think we should implement it because it's so dang simple, and it'll also be your first sorting algorithm, which anyone doing an algorithms class has to at least implement one sorting algorithm. So I do expect everyone to open up their editor immediately. Okay, you don't have to. I mean, you don't have to. But let's look up bubble sort. Open up bubble sort, and it comes with an array, and it's of course a sort in place algorithm. So hopefully everyone can do this, follow along. So again, remember our algorithm. We need to be able to translate the ideas in our head into code. So what I'm going to do,
So we need to start from, we don't need to go to the last one.
And let's just kind of think about it in the abstract terms.
Because we are going to check the next one, so we don't need to go to the last one.
And we need to start at 0 and go up to, but not including n.
J will be 0, yeah.
Because of course,
But J will be less than array dot length minus 1 minus I, because as we increase the index we don't need the last ones. J plus plus. Now of course I've done this before, so it is easier for me to do. Now if AR bracket I is, well,
Okay, so that seems pretty easy, right?
let's think
So we're going
about
to go for I up to, say, n, right? That's our thing. We need to do this n times, right? We got to keep on bringing that number down until it's 0. And that means our inner loop needs to be the one that's actually going to be doing the special magic and doing all that. So it needs to go up to
n minus 1.
But remember, every single time we do a loop,
We don't need
the last item
minus
is
I.
sorted. So we go to n minus 2 for the second case. We go to n minus 3.
Yeah, that's nice.
Etc. And from that point,
So now what do I check? I need to check if the value of J and if the value of I. What do I need to do? So let's try to see it, right? Let's remove that. So pretty much we have an array. Let's make it black if I can. Now I will add some text. That's fine. So we have 2, we have blah, blah, whatever. So this is our array. Now what will happen is we will start the loop. I am here, perfect. And so first loop is going till what? Till here. So I will go through each and every element and I will check if it is greater than the one, then we will just replace them. Oh, I see. So I need to do ARJ is greater than ARJ plus 1. So if the current guy is bigger than the next guy, that is not good. So we will sort them, or I should say replace them. So I have replaced these things like 100 times. So I will do AR bracket J. The current thing will be equals to AR bracket J plus 1. And the J plus 1 will be equals to J, that is temporary value. So most likely this should do the trick. I hope it will. And let's just find out. Bubble. Let's see how it goes, and let's watch the video meanwhile.
The only thing we have to do is do a simple comparison, right? If I and J, that's really all we have to do, right? I mean,
If I is greater than J, I is greater than J, then we swap it. And what I did was J and J plus 1. Am I done? Let me think about it. I think I kind of tried to mix bubble sort and selection sort. Maybe. See, let's try to see what I'm actually doing here. I'm going to run this loop for every element except the last one. Now, when I'm at the first element, I will start from the first element. I will go till the second last element. And I will check if the current element is greater than the next one. If it is greater than the next one, then it will become the next one. So next time I'm going to check it again if it is da 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 da. So this makes sense, but is it really selection sort or is it really bubble sort? I think it is bubble sort. It sounds like that to me, but let's try one more thing. If bracket I, wait, isn't that the same thing? I think it is the same thing. Let me try it really quick. Just give me a second. I will try something real quick. So let's try to visualize this. My I will be 0, then I will go through j. So if the value of I is greater than j, then what will happen? I don't think this should not work, to be honest, but let's see what happens. If this works, I will like to try this as okay. This failed. Yeah, that should not make sense, of course. That should not make sense. Anyways, let's see.
That's the extent of the algorithm. It's an extremely simple algorithm. There, I'm positive. So let's go here. Let's do also the last element, the first iteration, because we're going to do a +1. Remember that. So let's -1. Then remember, every single time we execute, the last element becomes the largest element. We don't need to redo that. So we're also going to minus I. Does that make sense? There we go. We've now translated this code into the. Now we need the swap. Swapping, always not all that bad. Constant.
Oh yeah, he's doing that as well. J plus 1.
Whatever your first line is, you just repeat array j equals array j plus 1. Copy that and go array j plus 1. Can be Michael Bublé. You sure than there are cover recursion. Is everyone pretty excited about their first sorting algorithm? I'm excited. All right, there are other sorting strategies I want to talk about, but sorting algorithms are going to deal with recursion, and I haven't recovered recursion yet, and really understand it until you completely painful concept. All right. Any questions? I've only ever had to implement a sorting algorithm one time. So
Nice.
very, very rarely.
Since we are comparing each element of an array with another element of an array, it's kind of n square. But I just didn't understand that n into n plus 1 by 2, how did we came up to
Oh, yes.
came up to that?
So the first part of your question was we're comparing two elements of an array, so that's n squared. But how did I come up with that formula and all that? I can go over it one more time. So remember, that's why I did that very fundamental thing. When you access an array, what is the runtime of accessing an element in the array? It's that fixed computational cost. So it's O of 1, right? Every time you access is O of 1. So if we access an array twice, it's just
O of 2.
constant, right? So this is all constant operations. Everything in here is constant. So this part of our operation is constant. Nothing in there is based on input size. It's all constant. It's really just these two that cause the squared algorithm, because we're going over the length of the array, and every time we go over it, we go over some or most of the array every single time. So we go over n. So now how does this thing, we can go back to this proof. So I'll just kind of go back to the simple version of it all. Remember, I'll just kind of re-explain it, just because the reality is we're doing nothing different than summing all the values. Because if you think about it, we're going to run n times the first time. Actually, well, technically the first time we run n minus 1 amount of iterations through the loop. If you look at the code, we're running, the very first time we were running n minus 1 amount of times. The next time we run n minus 2, because I becomes 1, we subtract that off also. The next time we run n minus 3, and we keep doing this all the way until we get to 1. Right? So if we sum all these numbers up, the way to be able to sum this, of course, is via that formula that I showed you. And so that's how many literal steps we're going to take. And so there you go. We could replace this technically with n minus 1, right? N minus 1 multiplied by n minus 1 plus 1, right? I did a bad job. But again, yes, there's still going to be an n squared somewhere in there, right? Like if you just use FOIL, you'll see that it n squares eventually. There you go, you have it. So the actual real running time is n squared minus n over 2, and then break that all off because insignificant factors, all that, it's still n squared. Does that make sense? So nothing really changes. I just tried to keep it pretty simple. All right. Well, I think it's a good time to move forward, right? Oh, we got one more question.
What's a good sorting algorithm for immutable arrays? I assume all allocations for bubble would be deadly.
Well, the thing is that if you create an immutable array, you have to come to it with the fundamental understanding that you are creating an exceptionally poor performing data structure. Immutability is supposed to come with the ease of use, but it comes at the cost of space and replicating space. And so yes, computers are extremely fast at memcopy, but that means you're doing n operations over and over again. So if you were to literally do that, the worst case scenario is that you have a reverse sorted array and you try to bubble up. That means every single time you did that, you'd have to bubble, which means you'd have to copy n. So it'd be somewhere in the n cubed, if not higher. And I'd have to think about that, but it'd be a very poorly performing algorithm. I also would never use immutability and sorting in the same sentence because that just seems like it's a terrible idea for performance.
Okay.
Your computer would chunk really hard. All right, so we're actually on to the second data structure. Is everyone filled with exuberance, joy, happiness? Okay, good. So I did say something weird earlier, of course, which is this statement in JavaScript is not an array.
Is Bun a good alternative to npm? I will say yeah, npm install, you can replace it with Bun, that's fine. Or if you are actually using Windows, just wait for some time. Bun will hopefully soon support Windows. Then you can also replace Node at a smaller level, and maybe in few years you might even replace it with Node. But yeah, you can totally use it as a yarn, like just for installing packages as a package manager. It's quite cool, but not for Windows yet, so might need to wait for a while for that. But like, it is not really needed. Like, it is very nice, it is cool and stuff, but it is not like a very essential thing, I personally believe, because like it installs things very fast. That's awesome, but if that's the only thing it does, it's kind of a personal choice. Like, do you really want that speed? Is it really that fast? Like if you're on Mac OS or Mac OS or Linux, then it might be that fast for you, but on WSL on Windows, it is not that fast initially. But of course, when it is reinstalling or something, then it's fast. But yeah, not that much of a significant difference maybe. So I will personally wait for it to actually support Windows a bit more, so I can actually use it for my simple node stuff like running code. Like basic things it should be able to cover as far as I have seen the YouTube videos. So we just need to wait for Windows support and bam, we are good for small and medium basic things. But they do say that we support Byte, we support Jest, anything, Nest.js. If they do it, that's cool. Otherwise, not really.
Solid definition and understanding of an array. Let's see, is this thing an array? It's not an array, right? We can tell it's not an array because you got .push. You can grow it, right? It can grow ad infinitum, right? So something's happening on top of an array minimally, right? Can we at least say that?
Yeah.
That there may be an array underneath the hood somewhere, but somehow we have the ability to add, we have the ability to insert, we have the ability to delete from, in which all the indices are actually being adjusted. Because if I shift an array, the first element in the array becomes the 0th element.
Okay.
So therefore, something had to happen, because surely arrays don't offer that sort of organizational structures, and Linux is the only machine around it is happening. All right. So I'm sure some of you are getting pretty offended by all this talk. Yes, I'm going to say HTML is not a programming language. NeoVim is the greatest editor. Rust is the greatest language, and Linux is the only machine you should develop on. Hot takes for everybody. But let's keep on going. We're going to go to our first real data structure. The reason why I'm calling it the first real one is because arrays just don't feel real in some sense, right? They're so raw, they almost feel like a primitive of computing, right? They don't necessarily feel like they're something. But I mean, there is a lot of things happening underneath the hood. Nonetheless, it still feels very raw. So let's keep on. Oh, let's go. I did have this funny joke in here, which is it's available in pretty much every language except for JavaScript. Anyway, so what sucks about an array? Deletion. Well, you can't really delete, right? You can zero out something. Insertion. Well, you can't really insert. You can write. it's ungrowable. Why? Remember Fred, F's in chat for Fred because F went away. So let's talk about linked lists. Okay, so this is really our first real data structure. They often call this a node-based data structure. No, not node as in the runtime for JavaScript. Node as in the type of container that will wrap our data. So let's talk about this. This is pretty fun. This is where things I think get really fun because now we're actually getting into really the heart of the beginning, like you're going to see data organized in such a way that you will not only be able to visit, say, this node, it will point
To the next node. Yeah.
Which means that things like get I obviously work a lot differently, right? You can't just get the ith structure. What would you have to do? Well, if you start here, if this is our head, our first element, we literally have to go, okay, 1, 2, 3. All right, we wanted the fourth item or the third index. There we go. We just got it. We can return out this value. And the reason why I draw circles around this is that it's often a containered item, meaning that you hand me a value t and I put something around it. So that's why I call it a node-based one. So imagine you have a type definition in TypeScript, which is generic over t. What you'd see is a value, which is going to be of type t, and say a next, which could be an undefined value of another node.
Okay.
Oh my goodness. So this was the first algorithm that blew my programming career that I can really tangibly remember, is being able to see this in my head and how it worked. And yes, I did see in Java at that point. Please don't make fun of me. But that's just how it was, you know. Everyone's first language is sometimes unimpressive. So
Mine was also Java. Coincident.
Fundamentally works is that you have a node that contains a value and a reference to another value or to another node. And so that way you can walk this daisy chain, if you will, of nodes which contain values. So this would be considered a singly linked list. Why is it considered a singly linked list?
Because it doesn't know what is back.
B points to C head and just can tell that though it references data that still is alive, it itself has no references left, therefore dead, right? Marketing bidirectional arrows right here of numbers. Instead of as it can be very all we have to say TypeScript, right? Performed thing is based on instead is constant time, right? It's an offset into the object, sets the memory, boom, boom, boom. There we go. So if we set two nexts, right? Because we set A's next to be F. Well, let me write it down here. We set A's to be F's. We set F to be B. Then we have to do the two previously. We do B has to be set to F, and F has to be set to A. All those operations are performed constantly, right? It's just setting a property. Therefore, to insert inside of a linked list at a given position is O of 1, right? Nothing is based on input. No matter how big the value you give me, no matter how many items are in the list, none of that matters. It only matters that I have to break 4 links. And yes, those each can take some amount of time. That's why, like I said, there's always a constant. We drop the constant. It does not matter that there's a constant. Practically speaking, constants can matter, but in this case, it doesn't matter. So there we go. What would we have to do? We're able to insert. So let's think about in some constant time, or we just had access to C. So we're not C, which points to D, right? We're gonna actually have to point through C's next to D, right? So we're gonna have to go back, take its next, and point to my current one's next. Code sense if you have C next. Does that make sense? Like what I just did there is I broke the link from B that points to C, and I now point it to D. That makes sense, right? I think that makes sense.
Would you put C next, or why not just put D?
Well, the thing is, you have to first get access to D, right? So
And for that, we just do C.next.
D equals C.next, right? Then I could replace that with D. So that is equally valid as well. But remember, we're now using memory, and we're now playing around with these linked lists. So it does require us to be a lot more specific at all points. Hopefully that sort of makes makes sense? I mean, this is obviously a very hard concept the first time you see it. Double separation. So here, now that I think about it, we've taken it out of the graph, right? We're deleting C out. So yes, D and B now point to each other. Therefore, anything, and now requires going. So therefore, deleting is constant time. Then you have a linked list.
Very interesting.
We've already talked about this, insertion, deletion. And now you can understand that if I were to get a value, I'd have to walk the list, right? So if I ask for the 5th value, there is no way when we have this type of structure right here to get the 5th value. I literally have to write a loop that's going to be like to the correct value, everything. So in general, getting head or tail, all those things, they can be pretty good operations. So head and tail is a unique get, because in the sense that if our linked list implementation has a single reference, head, that points to the first item in the list, getting head can become a constant operation, no matter how big or small the list is. Getting tail can also be a constant operation, because again, we already have a defined pointer to that. It works every single time.
Okay.
All right, so deletion, of course, deletion at the front or the tail, right, the head or the tail, it's actually, again, constant operations, is it not? Because if you think about it, all you have to do is
change the property
and do the deletion algorithm. Take this, do the deletion algorithm. But if you get in the middle, or you delete in the middle, you have to traverse to that point. So you have a 2-operation cost, the traversal plus the deletion. So deletion from the ends can be constant, but deletion in the middle can be costly if the traversal is costly. But the deletion itself, of course, is not costly. Prepending and appending, constant time, again, because you are able to insert and just break the links from head or tail. So that's very, very fast. But insertion in the middle, it's the traversal, again, that can get you. So long as you can traverse fast, your insertion is fast. So this is kind of like the weakness and strength of a linked list, is that, yeah, it's a bit more complicated, whatever you want. All right, so I don't think we're going to implement this just because time is running out, and I think it would take us, it's just a very heavy operation. You saw the next and all the previous's. But in general, this is kind of an interface that you will see if you use that Kata program that I built. This is effectively, I believe, the exact interface that would be used in the linked list, which is just like here. Here's all the operations you expect it to be able to do. Now program the underlying. We do have one question.
I believe the insertion of F after A is arbitrary. You usually will append F either at the beginning or the end of the linked list for constant time.
So the thing is that it just depends on how you're using the list. If you insert at the beginning or the end, you have a constant time guarantee as long as you have a reference to both head and tail, or depending on which side you're inserting on. But if you don't have the reference to the node directly, it's the cost of the traversal to that node, and then it's the cost of the insertion, which is constant. So traversal is where the big thing comes into play here. It'd be time you do it. For us, we don't have to worry about that. So in general, I can't tell you how to use a linked list because you use a linked list how you want to use a linked list, but I would strongly recommend not traversing. Anytime you do an n-length algorithm, there's probably a data structure that's better at it, right? That makes usual sense. Sometimes that's as good as it gets, right? But for us, we don't have to worry about that. All right, so why did I start with linked lists? Well, they are super foundational. In fact, but linked lists are like the most fundamental unit. And long as you understand how to traverse and move around in a linked list, you're going to understand all these other data structures.
Code it? Or do I just code it myself?
We're going to get to the point where we're going to run into, is this an algorithm or is this the data structure? Well, it uses the data structure and then performs an algorithm on top of the data structure. So this becomes a more common theme we're going to see. So is linked list a data structure or an algorithm? Well, you could argue that the insertion is the algorithmic side of it. The actual setup is the data structure itself, right? We can make these arguments, blah, 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 blah. I'm not going to be pedantic.
I guess I need to make it myself. So let's do. Let's think about it. So we have a linked list. We have a doubly linked list. Amazing. So I guess I need to start by defining a node class. That's the. Let's check the test, to be honest. So we have a singly list, then we are just testing it. We are doing append. We are getting it. We are removing it. You're getting the list and blah blah blah. Array test, global.d.ts list node. Yes, sir. Declare interface list. Yes, sir. I guess I need to define a class, right? Do I do it in the same class or do I make a new file for it? That's a dumb question. This is painful.
Call it whatever you want. I'm not going to be offended. All right, so our first data structure on top of a linked list is going to be a queue. This is one of the most common data structures I have implemented. I've implemented a queue just this year. I had to shove video down into a video decoder, and the only way to have a buffer to be able to do this and make sure you insert it in the correct order is first in, first out. And what is that? That's a queue, right? And I was using it in C too, so I felt extra, I felt a little bit smarter than everybody else writing C linked lists. It felt very good.
Yeah.
So let's go over a queue. So we know that, so that way I can say Bravo, Charlie, and Delta. Let's see, Bravo, Charlie, in a queue. Well, before we go to that, a queue is simply a FIFO structure, a first in, first out. This is what the Brits call a line. So to point to E. Does that make sense? So it would be kind of a two operation. You could imagine, I'll just write this in actual TypeScript, equals E. Does that make sense? We break this link. We are now pointing to the end of the list. Awesome. This makes sense. But a popping operation, we don't pop from the tail.
We pop from the head.
Now also notice that I'm using a singly linked list. We don't even need a doubly linked list. We don't even need that extra computation time. We don't need that extra property storage requirement. We need very minimal amount of stuff. So a head, if we want to pop it, we do the exact same thing. We would first set head to point to B. So we're doing the reverse operation. Head points to B. We'd save off a reference of head, of course, right? So we'd have some sort of const head equals the current head, right? We point head to B, and then we can just simply take the old one, remove the link, and then return
This is
a node-based data structure, which means we have a container around the value that you hand the queue. So therefore, we have, without using set it to then set our saved off reference to null, and then actually shocking the way around, we'd lose the value. Then what it's doing is constraining what you can do with a queue. And by constraining what it can do, what kind of performance are you getting out of queue? When you add to the end, what's the performance? Well, we don't traverse anything, right? We don't go over any sort of list. It's not based on how big of a value you give me. It's simply based on the fact that I have to set one and creating one next value to a new node, and I have to update where may require me to go out to the pushing, and we've made sure that it's very, very fast, and it performs a specific, which is peak, the ability to see what is my first element without popping it off. Of course, that would just be, hey, head.value, right? That's pretty much as straightforward as it gets. And so, of course, I already said this part, we're entering into the world where we constrain things. From here on out, you'll just notice that most things are constrained intentionally, such that we get very good performance out of it. You can only use it in a certain way. Yes, it is technically a generalized linked list underneath the hood, often with a queue, but you can only use it in a certain way.
All right. Nice. So I spent 2 hours today kind of like revising what I already read. Tech is already something I know. Recursion is somewhat I already know. Quicksort, no idea. Oh, this is here, the linked list part. I already know a bit of that. Trees, I don't really know much. I partially know these things, I can likely do them, but yeah. Heap, no idea. Graphs, what the fuck is that? Map, okay.
It has a length that has a number. We have availability for constructor. We have enqueue. So this is typically the phrase that is used when implementing a queue. Is to queue something.
It's like pushing, right? Yeah.
Add it to the queue or push it to the queue. And then we'll start constructor, and then we'll have a queue node that is, say, generic over T. And we want a value that is T, right? And then, of course, we're going to want a next that may or may not exist, right? We don't know how many elements we have. I can't remember if node is taken. Is node taken? I think it, okay, cool. At one point, you couldn't create node. It would actually fail on you. I don't know what's changed or why it's changed, but there we go. Awesome. We have type node. It has a value. It has a next. This. And of course, this can be undefined as well, right? In TypeScript, you can always use the old question operator, or whatever it's called. I forget what it's called. And then we can go tail as well. Ooh, that's teal. There we go. So now we have our two references, right? They
Yeah,
are
yeah.
defined, but we have two references, one to head, one to tail. They're of node t, generic, or of node generic over t. This dot head equals this dot tail equals undefined. Look at that. We're going to be super serious about this. Now, of course, length, we have nothing in there, right?
Okay.
Awesome. We've pretty much done the hardest part about a queue. Okay, not the hardest part, but one of the hardest parts, getting your constructor quickly. All right, let's start with peak, because peak.
Oh shit, I forgot. This is TypeScript. I can just literally make an object without making a class. So we don't really need to worry about bullshit. That's what this guy is saying, right? So I have to declare a node. It will have a value that is t. Now I will need to make that like that. Bang, bang, bang. Bang, bang, bang. Now after that, need to define a few things, I guess. Node t, instead of length, this will be head question mark tail. So first of all, peak is the simplest thing ever, and I'm just going to do return this dot head question mark dot value. Right, that's the easiest thing we can do. Now I will finish the constructor as well. That's also somewhat of bullshit, I will say. Well, this line is kind of useless because it is initially null / undefined anyway. So why do we need to define it as undefined? Maybe just to look cool or just to make sure it is undefined. I don't know. He did it. I will do it. Otherwise, technically speaking, we can just define it here as well, right? But okay, not a problem. Now, if we are trying to enqueue something, that means we are trying to adding something. We are trying to add something. What the fuck is wrong with my English? So anyways, what we do is we will do this dot tail dot next is equals to item, right? And what if the tail does not exist? That's an interesting situation. Oh man. Let's see. So I guess I can just add a condition like if not this dot tail, then we will do this dot tail is equals to item. What's the problem? Oh, my apologies. My apologies. I can do this. Next will be null, doesn't matter. Otherwise, we will do this. This dot tail dot next is equals to value will be item and next will be nothing, and then this dot tail is equals to this dot tail dot next. I guess, I hope. Learning about algorithm, I'm going to need to do something motherfucking all right. Hopefully this works. Maybe it doesn't work. Who knows? Who cares? Or I can just define it as an item right here, but that's bullshit. Doesn't matter. So if we're trying to dequeue, we are getting the first element, right? So I can just return head dot value. And my friend, if first of all, if we do not have this dot head, we return undefined. Now, otherwise, we will do head is equals to this dot head, and then we will do this dot head is equals to this dot head dot next, and that should this should be something. This should work, right? Let's find out. Let's find out. By the way, the thing you are coding. Yes. Yes. Are you trying to say that I should do something like if, like you want me to add if conditions here, like Java, like you want me to do something like this? If not this dot head, then we return undefined. Otherwise, we return this dot head dot value, something like this. I mean, I can do that, but still the same thing, right? Like it's kind of easier on me if I do it this way. Like otherwise, why will I use TypeScript if I want to do everything like something cool as Java, C#, blah blah blah. Burn is not like a replacement for npm, especially if you cannot bundle some frameworks, right? Or it too. I have no idea. I never used it, but it failed. Nani, list.enqueue failed. Oh my goodness, I have failed myself. That's very interesting. List.dequeue should be equals to 5. Let's try to run it myself and find out what's up. So first of all, I will make a new queue, right? And I will just make it based on number. Now, what do I do, son? I can just console.log queue always. Console.log the queue. After that, let's do the functions. Queue.enqueue 1. I will console log everything because why not? Console.log everything. After that, I will like to dequeue. I will like to dequeue 3. Oh, dequeue doesn't need a number, my bad. And I will like to enqueue few more numbers, 3 and 5. Now I will like to enqueue 8. I will like to dequeue once more. I will like to peek as well, to be honest. Let's try to peek. And let me add a bit more information here. So like first, and then we are enqueuing something, right? Let's just do this. Right, that will be easier on me. I can dequeue and then log the queue. I can enqueue, log the queue, dequeue, log the queue, peek, and log the queue. Okay. Let's see how this goes now. Let's see. So queue copies the relative path, burn, paste, change this to dot, back. So we have a lot of logs. Let's see how it goes. So initially we have the first head and tail is undefined, perfect. Then what we did was we enqueued one that is void, so it says undefined, that's fine. Now when we are queuing, I can't even pronounce that. As you can see, the tail is that, but the head is undefined, and that is not very nice. So we need to do something like, if we do not have this dot tail, then this dot tail is equals to that. But at the same time, if we do not have head, okay. So first of all, I will say const child is equals to value will be item, perfect. Now what I'm going to do is, if we do not have the tail, do this. If we do not have the head, do this. And here I will add a condition called else, and let me just put it right there. I think this is nicer. This should work hopefully. Let's see how it goes. Okay, let's see the logs now. So with the initial enqueue, everything is 1. The head and tail is 1. Next time the tail should be 3. Nice. Next time the tail should be 5. Nice. And then I dequeue. Dequeue should return 1. And the head should be not undefined. It should be 3. So why is that not the case? Why is that not the case? I wonder if that's correct English. Let's think about it. So what am I doing? I'm saying that head is equals to this dot head, and this dot head dot next is that, blah blah blah. But the issue is whenever I enqueue, if we do not have the head, we do that. This dot tail is equals to that, right? If we do not have that, but what if we do not have the next? That's a good question. What if we do not have next? This dot tail. Let me think about it. What should happen when I queue something? Let's think about it. Let me first of all delete everything. Blah blah blah. So this is our queue, right? I have a head and I have a tail, right? So I will add a value. Let's say I will add 1. Now initially head should be 1, tail should be 1, and head should refer to tail. Is that right? I think that is right. Let's put it there. Let's try this. Next is equals to the tail. Yeah. Let's run the code again and see how it went this time. Something better, something worse. Let's see. So this was quite fast, as you guys might have noticed. So this time the next value is 1. Is that good? Like that is the head, that is... No, that is not really good. It should be that if it is not that, right? Obviously. Next time, head is that is that. Okay, so that was a mistake, I will say. That's not really nice. Let's think more. Now, I will enqueue something else. I will add 2. What should happen now? The tail should be changed to 2. The head will still be 1, but the next will be 2. Right. So this means I should do this dot tail dot next is equals to that, and this dot tail is that. Right, that is fine. So if that is that, blah blah blah, that's a very interesting situation. Let me think more about it. So we have the tail, and the tail is equals to that value if tail does not exist. If tail exists, then the current tail's next will be this child. So I will change it to child, and then the current tail will be equal to the child itself. Right. That's right. That is right. That's totally right. Now, when we do not have a head, the head should be equals to this, and the tail is equals to that. Right. But in the next case, I will have both head and tail. I'm making it so that the tail dot next is that, but we also need to refer the current tail as the next or the head. So we need to somehow say that this dot head dot next is equals to this dot tail, right? Ah, that's very interesting. Let's watch the tutorial more. I think I should have read some books before, but that will be useless here.
Now have fulfilled our that it serves up to it. So couple operations. We need to do some bookkeeping. This dot length minus minus, right? If we want the outside world to know how many items.
Oh yeah, I forgot to change the length as well. That's kind of essential. My bad. This dot length plus plus. This dot length minus minus.
We kind of need to keep track of these things ourselves.
Okay.
You're usually used to something like an array doing this for you. We are now the array, right? We are now
Yeah.
doing. Let's go like this. Const head equals this dot head. This dot head next equals, oopsies, wrong direction. This dot head equals this dot head dot next, right? So we saved out our head. We've updated our head pointer to the next one. Whether it's undefined or not, it does not matter to us.
Yep.
We just updated it to the next one. Go
Yep.
free here on bookkeep. All that hard? No, it's really just those 2 simple steps. Save your head.
Okay, I will free it as well if you want. Okay, not a problem.
That's 2 simple steps. Index 0. I'm not off by 1. I'm still correct. Oh dang it, we have to reduce our length. Okay, I am off by 1 in index zeroing. So there we go. So let's do enqueue, right? Which is really the opposite operation. We're going to go to the tail this time instead of the head. So again, if there is no tail, that means we pretty much have an empty array, right? Now, if you're using a more, if you're using a different type system, I would probably have chosen this dot length equals 0, right? Because at this point, I could say, hey, we do this operation when this length is here, but since TypeScript can't understand exactly your meaning if you don't intentionally check for null or undefines,
Yeah.
then we're going to check intentionally for undefined. So if there is no tail, that means this dot tail
Is equals to that new child.
head, which equals a new node.
Oh, that's the mistake. This way I will no longer need this part, because if we do not have a tail, we do not have a head. In that case, we are just defining them to be this damn thing. Otherwise, I'm saying the tail, then we don't need to worry about redoing the things ourselves. That's very nice. That's very beautiful. Let's see.
So let's create a new node. Value is item. Whoopsies. As node generic over t. Right. There we go. We've now just created the node. Our next is undefined. Our value is the item. It's of type t. Our node is generic over t. Everything is good except for one thing. We don't have our length correct. So this dot length plus plus. Make sure you spell length correctly. There we go. This is looking pretty good, right? We now have it a value. Really, we could just take this right here. So we've just took our tail and added a new one to the list. So now we just need to take our tail and point it to the new one, right?
Yep.
Right. Yes, you're absolutely correct. Thank you. There we go. Our tail now points to the last item in our list because it became the last item, and then now we are pointing it correctly. So that is all that is required to do a queue. Queues are actually fairly simple data structures, right? They're not too hard. You're only managing one link. You just have to correct. So that is all that is required to do a queue. Queues are actually fairly simple. It's a great time to ask questions if you don't feel like you quite get it.
In line 6, you're saying that if there is
Oh, 6 up? Sorry, I use relative numbers. Are you saying 6 up right here?
Yeah.
Yeah.
So when there is no tail, that means that is there one node or there's no node at all? Like
There's no node at all. So normally what I would do is I do something like this, right? This dot length, whoopsies. Oh yeah, we can do that. This dot length equals 1, meaning I just got done adding it. But of course, what happens right here, TypeScript is like, hey man, right? It can't handle that, so therefore I have to do that. And dequeuing, of course, is if this dot length equals 0, then this dot tail should equal undefined, right? We need to make sure that we forget about it at all points.
Yeah, that's okay. So I'm undoing something, and in that case, at the end, I have to see if the length is 0, because I'm changing the head value. I'm changing it to the next, but I also have to change the last thing. So let's say if we dequeued the last thing, that means we have to say that this dot last no longer exists, right? Is that right? Oh, sorry, it is called tail, my bad. So if I run this, it better work. And let's get back to the video.
So a little implementation detail, but so then this thing of course falls apart. It's like, hey, I can't do it. So I didn't want to just be encumbered by TypeScript types, or really TypeScript just actually technically doing the right thing. There we go. And so for that, I just go not this dot tail. There you go. Awesome. It's the exact same check, right? Long as we've kept everything. So the peek method is very, very simple. So right now, if we just take this as our list right here, and we wanted to peek into our list, meaning we want to see the next value returned without mutating the state of the queue, all we're going to do is go to our head and get the value out of the head. There's about 2. So if we wanted to insert f into here, we have to do 2 operations.
First of all, e.tail.next, it will be linked to the next one, and then the linked list tail will. Yeah.
Always represent the end. Stack. I know, obvious. It's very, very, very obvious. Oddly enough, I've also created a lot of these things. These things are great for performance. Technically, with JavaScript arrays, awesome to use. You can use push and pop at pretty much constant time.
Okay.
So let's talk about it. Let's go over it. Let's see how this thing works. And of course, we're going to be using none other than our beautiful linked lists right here. So I'm going to create another one of these. Zoom in. For those that don't remember, a linked list is a node like algorithm, which is going to have a value, which is going to be a t, and then it's going to have a next, and sometimes it will also have a previous if it's a doubly linked list. And of course, these are of type node t. All right, so now that we're kind of back into it, so if you can think about it, here I'm going to redraw our nice little list here, A, B, C, D.
I might even take a previous
What we're going to have is this is going to be our head. So it's as if we pushed in A, we pushed in B, we pushed in C, we pushed in D. Now the reason why you have to draw it backwards, I always draw it backwards because it's so much easier to draw it backwards, is you really kind of can think about this like till this. That is why the arrows are same thing at the Q way, which is slightly different. And then you could Q very falling. Gid is called the stack for a reason because it is only going up and down. Else we don't return anything. And again, constraints. They're awesome. Constant. It doesn't matter how many items are on the list. It does not matter how big the value is. The fact is we are just simply setting things to null or setting them to point to different values. We kind of consider those constant time operations. Again, I know property access on an object in JavaScript may or may not be constant time, blah, 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 blah. We just don't think of it like that. All right. Though I did have an interview once at Uber in which the person made me not only go over all the running time, they're like, well, you didn't know that, accessing properties in JavaScript is log n. And it's like, oh, okay. Then if that's the case, then everything, just put a log n on the end of everything. He's like, well, then what's the running time of that? I'm like, well, you just put log. And it was just like the longest, most drawn out, make everything, add the word log n to everything. It was very annoying. So typically, we just don't do that. All right.
So let's try to push something, right? So I will just do this dot tail dot next is equals to, I will make a child.
All right, so let's go to stack and let's implement a stack.
I will do value will be equals to what? Let's think about it. So the value will be item, and then what will be the previous element, right? Let me make it as so I will get the suggestions. I will remove it later on, who cares? So the previous item should be equals to what? It should be equal to the tail. The next item, it does not exist. Now, let me just remove that. I don't like that. So this time, what I'm going to do is the tail's next child will be child, and then the tail will be equal to the child itself. Simple as that. But of course, first of all, we need to do this dot. Now we also have a situation in we do not have a tail, in which we do not have a tail. So if we do not have a tail, then this dot tail is equals to the child, and otherwise we can do all of this, right? So if we let's see what is happening. First of all, length is getting increased. Obviously, we have the child, the previous value is the tail. So if there is nothing in previously, it is null or undefined, and if there is something, then its previous value is that. I'm not sure if I should be using doubly linked list, but that's what I'm doing because I'm doing it from next. I can just use let's do it. So if the tail doesn't exist, we are defining it as the current child because it is the tail and the head as well, but we have no head, we don't care about that. And then we are doing the else. Otherwise, what we are doing is if the tail already exists, we are saying the current tail's next thing is the child, and then we are saying that the current tail is this child. Or I can just do this dot tail dot next, doesn't matter, same thing. Now we are trying to pop, right? So first of all, if this dot length is equals to 0, or I should say if we do not have the tail, right, if we do not have the tail, then we are returning undefined. Otherwise, we are doing this dot length minus minus, and by the way, we will remove we will give this, I will define it, to be honest, const tail is equals to this dot tail dot value, right? I will just do that. So I need to return the tail dot value, but when I'm popping it up, I also need to do this dot tail is equals to tail dot previous, and I need to delete the tail thing itself. How do we do that? We will need to look into that. I mean, one thing that I can do is tail.previous can be null, tail.next can be null. Is it necessary? I don't know. What's your problem? Of course, I can change it to undefined. Like these two things are, I'm trying to just clear the memory. So I'm just saying that this current node have no memory. Next is obviously not needed because it does not have a next because it is the end. So I can just say that previous is nothing as well. Let's see. So I will need to test the stack.
Bit different when we look like. Visualize this, which is the
Yeah.
and then I'm going to do previous instead of next. The reason why I do that is it just makes it a lot easier for me to visualize.
I have a feeling that it will not work now. I don't know why. It worked. That's crazy. So maybe I overdid something. We don't necessarily need next. Let's see where are we using next. So what is happening? If we do not have a tail, we are setting the tail as the child. Perfect. Then in the else, what we are doing is we are saying that current tail dot next should be child. If I remove that, what will happen? This dot tail is equals to the child, and child. Then I don't really need anything. I can remove all of that. Amazing. Let's look into this thing. If we do not have a tail, undefined, otherwise length is -9. Oh, so that was kind of like unnecessary because we are not actually going to look into the next value because we are never going to look into something which is not the end. So technically dot next was useless. That's what you are saying. Very interesting.
This, right? I draw the arrows
Perfect.
backwards. It helps me remember where I'm adding to. It just makes it a little bit easier. Again, we don't return this container to the outside world. Nobody else uses it. So you can represent it the way that is most convenient for you. And of course, it can be undefined, correct?
Yep.
So if it can be undefined, put the little question mark operator. Awesome. And then now we can go to our constructor. We have everything all set up. Everything's good to go.
Yes.
And let's start with peek. Peek is kind of a very simple operation. What is at the head? Okay. And they said, hey, how do we take this thing off? He's like, you shift it off. And this as node or else TypeScript. So we're going to have to take head and let's point to it, right? Point to the head. There we go. First step done. F is now pointing to E. Now let's make the head point to F. Let's go container, right? We can kind of do this, but of course, again, TypeScript does not like this type of programming. Even though we understand what is happening here, TypeScript hates it. So this time, instead of doing it that other way, I'm going to do it like this. Because I don't know. You can do it either way. This works out, right? We know what we're getting ourselves into. All right. If that's not the case, well, then we need to actually detach the head. So let's go over that operation one more time. If we were to detach F, what do we do? Well, the first thing we want to do, save out a pointer to F, so we can now access it. We're going to jump in here. We saved out the value that is pointing to TypeScript again, still battling us, going, hey, are you sure you want to do this? So we can actually just use our actual head reference right here. Right? That also works if you want to get rid of it. We're already pointing to it. Awesome. And then lastly, we on memory. Rust, you successfully, because it's too hard, if you're using C++, you'd have to free it. All right. It's a good joke. There's a joke somewhere in there. It's pretty good. And I believe this is pretty much everything we have to do to successfully have a beautiful stack. So let's see if this actually works out. Let's go npx jest stack. Oh, look at that. So it did try to warn us. Obviously, it was very, very correct. And now I see the errors of my way. What's the errors of your way? What happened here? It's 0 after you keep popping, right? So if you keep popping, it's going to keep returning undefined. And I must have came in here and caused value. No, actually, the value was, or where was the problem? The value right here? Oh, I don't see the, oh, yes. We'll go like this. There we go. That saved us. I won't cast it as a node because we don't actually know if it's a node because you can keep on popping on an empty list. There you go. That's a TypeScript.
All right, I'm back.
There. My fault. This is surely disappointing because now I had my first non-first try. And look at that, first try. We got it very first try. How fantastic is that? We could edit that in post, right? Definitely got this first try? Okay, good. Just making sure. All right, there we go. So that is all a stack is. It's pretty simple. The steps are actually more simple than a queue, right? Because you're really only focusing on a single pointer head. To me, it just is the easiest data structure to implement. Very, very small amount of link breaking. It's pretty simple. Only difficult part, drawing backwards. All right, so we're going to keep on going here. And this is the part of the list, or a part of the class where we're going to do a little bit of comparing and contrasting. So let's think about the usability of an array versus a linked list. Something.
So we have array, then we have recursion. That is like 223 to 350, so 1 hour 25 minutes. Now, so technically tomorrow I can finish till doubly linked list. Then day after tomorrow I can finish the trees and probably the heap. And then day after that I can do graphs and whatnot. So I will say this should be it for today. Let me just take this URL. Let me put it here. This way I will not miss it. And thanks a lot for watching. It's been quite a few hours for sure.